Hello, fellow Sapiens. Whether you're lying in bed, driving through the dark, studying, or cooking something slow, this space is for you. Here at Sleepless Homo, we tell science softly. Prehistory, archaeology, history, geology, and time itself. Spoken without noise or certainty, just quiet curiosity. We're not here to sell wonder, only to share what we actually know. If you find calm in that, consider subscribing or leaving a like. It helps this small corner of deep time reach other sleepless minds looking for peace in facts. Tell me, where are you listening from tonight? Do you use these stories to sleep, to think, or to keep you company in the hours no one else sees? And if you drift off midway, that's fine. I've added timestamps so you can return tomorrow. This is soft science for sleepless thinkers. And as always, stay curious, stay calm. Imagine standing at the edge of the Grand Canyon at sunrise. The first light of day crawls down the cliffs, turning ancient rock into shifting gold and red. Somewhere far below, a line divides two worlds. Above it, the rocks are layered, patterned, filled with fossils that whisper of ancient seas. Beneath it, the rock is darker, crystalline, silent. Between them is a knife-thin boundary that holds the strangest truth on Earth. 1 billion years of history gone. No fossils, no sediments, no trace of the landscapes that once were. Just absence, pressed thin as memory. This thin horizon, stretching across continents, is called the Great Unconformity. It is not a crack or a fault or a scar in the Earth's crust. It is a pause, a missing chapter in the planet's own autobiography. To understand why this line matters, we have to learn how to read time without numbers. Geologists do not read rock the way we read a clock. They read colour, texture, grain. Each layer of sediment tells how fast a river once ran, how strong a wind once blew, how long the sea stood still. Over billions of years, the Earth recorded its own moods: floods, droughts, eruptions, and stillness. When one layer rests cleanly on top of another, we call it conformity, continuity. But when a layer of deep, ancient rock lies directly beneath something far younger, with all the ages in between missing, that is an unconformity. It is the planet's way of saying, something happened here, but I no longer remember what. At the Grand Canyon, that silence is enormous. The lower rocks, known as the Vishnu schist, began as sediments and lava laid down more than 1.75 billion years ago. They were buried, cooked by heat, and squeezed until minerals aligned like fibres in fabric. Above them rests the Tapete sandstone, formed in shallow seas about 540 million years ago. Between them lies nothing. The missing time is roughly 1,200,000,000 years, an unimaginable span when whole mountain ranges rose and fell, oceans opened and closed, and yet not a single pebble remains to tell the story. When early geologists first noticed this boundary, they realized they were looking at something bigger than erosion. Rocks always wear down, rivers always cut, but not like this. This was not a local event. Similar gaps appeared across North America, Europe, Africa, and Australia. The same thin silence, repeating itself across the globe, as if the planet had collectively forgotten a vast portion of its own past, and so they named it the Great Unconformity, a quiet monument to time unrecorded. If you trace your fingers across the canyon wall, you can feel the difference between the two worlds. Below, the rock is rough and ancient, a survivor of deep burial and pressure. Above, it is smoother, lighter, laid down in gentle horizontal beds by calm Cambrian seas. The contact between them is sharp. It looks almost deliberate, as though the Earth had been sliced open and rewritten. The truth is that billions of years of erosion planed the surface flat before the seas returned to deposit new sand. But to the eye, it feels like standing at the hinge between two universes, the Precambrian and the Phanerozoic, the unseen and the visible, the forgotten and the remembered. Geologists call this kind of gap a disconformity, when both layers are sedimentary, or a nonconformity when sediment rests directly on metamorphic or igneous basement. The Great Unconformity is both, a patchwork of missing time that varies from place to place, but always adds up to the same message. Time is fragile, even in stone. When we look at the rocks below that line, we're seeing material that once sat deep inside mountains long eroded away. When we look at the rocks above it, we're seeing the first sediment laid down after the world changed. It's like opening a book and finding entire chapters torn out, yet the story still continues. The mystery is not just that time was lost, but how it could vanish so completely. 1 billion years is 1/5 of Earth's total age. During that gap, continents drifted, atmospheres shifted, and microscopic life evolved quietly in the oceans. Yet the physical evidence is missing. It is as though the record of the planet's adolescence was wiped clean before adulthood began. Scientists still debate what forces could erase such vastness. But before we can ask how, we have to appreciate what it means for that silence to exist at all. Every rock layer is a memory written in minerals. Sedimentary rocks remember water and wind. Metamorphic rocks remember pressure and heat. Igneous rocks remember fire. But the gap between them, the unconformity, is the absence of memory itself. It tells us that even the most durable planet forgets. It does not mean nothing happened. It means everything happened and nothing survived the telling. Standing at the rim of the canyon, you can almost hear it. The Colorado River roars far below, cutting through eons of deposition. Yet the line remains unblinking, indifferent to our curiosity. We, tiny primates who measure time in decades, are staring into a billion-year silence and asking it for meaning. Perhaps that's what makes it so compelling. The Great Unconformity is not a mystery because it hides secrets, but because it reminds us how much the universe forgets. The first scientists to notice these erasures were working centuries before radiometric dating or satellite mapping. In the late 18th century, James Hutton stood on the Scottish coast at Siccar Point and saw something similar: vertical layers of red sandstone overlain by horizontal grey beds. It was a smaller unconformity, but it revealed the same truth, that the Earth is older and more complicated than any human text. Hutton wrote that he saw no vestige of a beginning, no prospect of an end. The Great Unconformity is that idea, magnified to planetary scale. When geologists measure such boundaries, they are not just counting years, they are tracing the choreography of erosion and deposition, uplift and stillness. They analyse minerals for isotopic ratios, measure grain sizes, read tiny structures left by ripples and tides. Each clue narrows the possibilities, but the line itself remains a horizon we cannot cross. Beneath it, rocks have lost their original textures. They have been heated, folded and recrystallized until all record of their formation is gone. Above it, the story resumes as if nothing happened. To imagine 1 billion years of erosion is to think on scales that stretch human language. Entire mountain ranges could rise from the sea, crumble to dust, and vanish beneath waves, and still we would be missing time. Erosion is not destruction, it is transformation. The atoms of those missing rocks are still here, scattered across oceans and continents. But their arrangement, the pattern that recorded climate, gravity, and life, is gone. What remains is the blank surface, a geological reset button pressed sometime in the deep Precambrian. The Great Unconformity matters because it anchors one of the most dramatic transitions in Earth's history. Above it lie the first widespread fossils, traces of animals, shells and burrows. Below it the world is silent stone. Whatever happened between them, it changed everything. Yet tonight, we stay with the silence itself, the missing, not the becoming. Because that silence is what defines the mystery. It reminds us that the planet's story is not a neat archive. It's a living palimpsest, always being rewritten, with more erased than preserved. Even today, scientists map the line with satellites and fieldwork, tracing it through mountain ranges and under deserts. It is not one uniform surface, but a mosaic of many, each formed at slightly different times, shaped by different forces, but together composing a single planetary amnesia. When you look at maps of the Great Unconformity, you see the ghost of an ancient world, edges of continents that no longer exist, mountain belts ground down to roots, seas that have long dried up. The line is not just a feature. It is a reminder that the Earth's past is not entirely recoverable, no matter how advanced our instruments become. Perhaps that is what draws us to it. We spend our brief lives trying to remember, to record, to understand. Yet the Earth itself is comfortable with forgetting. It lets go of entire ages without regret, then quietly begins again. To stand before that line is to feel both awe and humility, the awareness that even permanence fades, that even memory has a half-life. The Great Unconformity does not shout, it whispers, and what it whispers is this: continuity is an illusion. Beneath every record lies a pause, a silence, a lost connection. We live at the surface of one such silence now, walking on the thinnest film of time stretched across an ancient planet. The canyon below does not keep secrets out of cruelty. It keeps them because forgetting is what worlds do when they turn and weather and wait. We may never know exactly what vanished during that billion-year gap, but standing at the edge of that ancient divide we are allowed to ask. And that act, the asking, the wondering, is the closest thing to memory we'll ever have. Imagine this. Every rock beneath your feet is a clock, but not one built with hands or gears. Its ticking comes from the quiet decay of atoms that have been whispering time since the beginning of the planet. Before we can talk about the billion years that vanished, we first have to learn how to hear those whispers. The Earth does not keep diaries the way we do. It writes its memories into chemistry, into the slow fading of radioactive elements and the birth of their daughter isotopes. To read a planet, we have to learn the language of decay. About 4.5 billion years ago, the Earth formed from the leftover dust of a dying star. It was not born solid, but molten, a storm of metal, rock, and fire where gravity was still figuring out its balance. In that early chaos, elements like uranium, thorium, and potassium began to find homes inside minerals. They were unstable from the start, and that instability became our greatest ally. As these isotopes decayed at steady, predictable rates, they left behind fingerprints of time. The slow conversion of uranium to lead, or potassium to argon, is not just a chemical process, it is a clock built into matter itself. When a mineral crystal forms, it locks these isotopes inside like seeds in amber. From that moment, the countdown begins. Some isotopes decay quickly, others so slowly they barely change over the lifespan of the universe. By measuring the ratio of parent to daughter elements, geologists can calculate how long that clock has been running. The beauty of radiometric dating is that it doesn't depend on the surface or the sun or any human-made calendar. It is time measured from within. Each atom's decay is independent of temperature, pressure, or memory. It is the universe's most honest measure of duration. To make sense of this atomic ticking, scientists use a concept called half-life, the time it takes for half of a radioactive sample to transform into something stable. Uranium-238 takes about 4.5 billion years to decay halfway into lead-206. Potassium-40, on the other hand, takes 1.3 billion years to reach its midpoint. Each isotope becomes a ruler suited to a different scale of time. The long-lived ones measure planetary ages. The faster ones capture the fleeting stories of eruptions and cooling lava flows. But knowing how to measure time is not the same as knowing where to look for it. Most of Earth's earliest rocks have been recycled, melted, or crushed beyond recognition. The surface we see now is only a few 100 million years old in most places. The deeper story survives in fragments, tiny minerals that outlived the mountains they were born in. The oldest of these fragments are zircons, microscopic crystals of zirconium silicate that are nearly indestructible. They resist heat, pressure, and even the passage of oceans. Inside each one, atoms of uranium decay to lead at a rate so constant that it becomes a perfect clock for deep time. The oldest zircons ever found come from a place called the Jack Hills in Western Australia. They are over 4 billion years old, tiny, glittering time capsules that predate any known rock formation. To hold one between your fingers is to touch a survivor from the planet's earliest memory. Within their lattice, scientists have found traces of oxygen isotopes, suggesting that liquid water existed even then, implying that the Earth's crust cooled faster than once believed. A single zircon, barely wider than a human hair, can carry the record of the first oceans, the first rainfall, maybe even the first stable continents. These are not just minerals, they are diaries written in isotope ink. The process of reading them is meticulous. Researchers grind down rocks, separate out grains lighter than dust, and bombard them with laser beams or ion probes, The resulting data look nothing like a calendar. It is a scatter of numbers, isotopic ratios and decay chains. Yet from that scatter emerges order. By comparing the ratios of uranium to lead, or samarium to neodymium, geologists reconstruct the timeline of crust formation, volcanic activity, and even the recycling of the mantle. These methods tell us not only when a rock formed, but sometimes when it was reheated, eroded, or buried again. Each thermal event leaves a partial reset in the atomic memory. The planet, it seems, edits its diary constantly, but never fully erases it. This kind of dating might sound abstract, but it underpins everything we know about Earth's history. The age of the planet itself, about 4,540,000,000 years, comes from radiometric measurements of meteorites and the oldest terrestrial minerals. Lunar rocks brought back by the Apollo missions confirm that the Moon formed around the same time, probably from a colossal impact that fused memory and matter into one system. When we measure isotopes, we're not just dating rocks. We're syncing our sense of time with the universe's own metronome. There is a quiet beauty in how consistent these clocks are. Despite all the turmoil, magnetic reversals, asteroid strikes, continental collisions, the atoms keep their rhythm. They do not care if they are buried or exposed, frozen or molten. Their decay continues, steady as heartbeat. This stability is why we can trust them more than any human record. Carbon dating works for recent organic remains, spanning tens of thousands of years. But to understand the billion-year sweep of geology, we rely on uranium-lead systems, rubidium-strontium, and samarium-neodymium pairs. Together they create a layered framework, like multiple metronomes keeping perfect time at different tempos. Once scientists learned to read these atomic clocks, they began to piece together the structure of the planet's past using stratigraphy, the study of rock layers. Stratigraphy provides the order of events. Radiometric dating gives them absolute ages. The two disciplines together transform geology from storytelling into chronology. By comparing layers across continents, researchers realize that the same sequence is repeated, the same types of fossils or minerals appearing and disappearing in predictable order. The Earth, it turned out, had been keeping a global ledger all along. We just needed the key. The International Chronostratigraphic Chart, the master timeline of the planet, is built from these two intertwined methods. Each colour band on that chart represents not just rock, but rhythm. The slow pulse of isotope decay measured against the turning of sedimentary cycles. The Hadean, Archean, Proterozoic. These are not poetic labels, but intervals defined by the chemistry of minerals and the patience of measurement. Even the word Hadean, meaning hellish, now feels misleading. The oldest zircons show evidence of water, hinting that the early Earth may have been calmer than we once thought. Perhaps it was already developing the conditions for memory. To read a planet is to accept that time has many speeds. Some events happen in an instant, a meteor strike, a volcanic eruption, a landslide. Others unfold so slowly they can only be seen in retrospect. A mountain range grows, erodes and vanishes over hundreds of millions of years, yet its isotopic ghosts remain, encoded in sediments downstream. By measuring the isotopes of strontium or neodymium in those sediments, we can trace where they came from, which continents they once belonged to, and how they were ground down grain by grain into the sea. In that way, even erosion becomes a record. The atoms remember what the rocks have forgotten. It is strange to think that the most reliable memories of Earth are not written by life but by decay. The same process that breaks down unstable elements also preserves the story of everything that has ever cooled or crystallized. There is humility in that. Our species measures time in years, centuries and dynasties. The Earth measures it in isotopic ratios. Each atom's half-life is a promise that something beyond life itself remembers. We can never read the entire story because the planet keeps revising it. Rocks melt and minerals recrystallize, resetting some clocks while leaving traces of the old ones intact. A zircon might contain uranium-lead ages from 4 different eras, each corresponding to a phase of heating or pressure. To interpret that kind of layered data, scientists use multiple isotopic systems, comparing the decay products of uranium, thorium, and potassium to untangle overlapping histories. It is less like reading a single diary, and more like reconstructing a library from fragments scattered by wind. This reconstruction extends beyond Earth. The same methods have been applied to meteorites, lunar samples, and even Martian rocks delivered to Earth by chance impacts. The consistency of decay rates across the solar system confirms that physics itself is steady. The isotopic memory of matter works everywhere, under any gravity, in any star's shadow. When we read the age of a rock from the Moon, we're also confirming the reliability of the clocks ticking inside the atoms beneath our own feet. Sometimes, in the lab, researchers speak of closure temperature, the point below which a mineral becomes a closed system and its isotopic clock starts counting. Above that temperature, diffusion of atoms resets the clock. Below it, memory begins. The idea feels poetic. Every crystal has a temperature at which it starts remembering. The Earth's crust, as it cooled from molten chaos, must have crossed countless such thresholds, billions of tiny memories beginning simultaneously. Those first zircons that formed, surviving from that era, are not just inert debris, they are the planet's first recollections. Understanding all this is not about blind trust in numbers. The methods are constantly checked, compared, and challenged. Scientists cross-verify isotopic systems, test decay constants, and account for contamination. Yet even with the best techniques, there are uncertainties, small ones, but meaningful. Radiometric dating does not hand us absolute truth. It gives us the most consistent map we have through an ocean of deep time. The fact that different isotopic systems agree across billions of years is one of the quiet triumphs of modern science. It means that, despite our brief existence, we have found a way to listen to the heartbeat of stone. Before we can talk about what the planet forgot, we have to marvel at how much it remembers. The zircon in a laboratory dish, the isotope ratio in a mass spectrometer, the faint signal of helium diffusion. They are all echoes of a time before continents, before oceans, before even the idea of erosion. The first 1.5 billion years of Earth's story are not lost because we have these atomic witnesses. They allow us to reconstruct the shape of vanished worlds, the cooling of magma oceans, the cycling of crust and mantle, and the first appearance of stable water. To read a planet, we listen for what changes and what stays constant. The atoms change, the laws of decay do not. That balance between transformation and persistence is what makes radiometric dating more than a tool. It is the philosophy of geology itself, that even in the face of endless change, something endures. So before we chase the mystery of the missing billion years, we first learn gratitude for the clocks that survived. They are the reason we can say with confidence that the Earth is 4,500,000,000 years old, that the crust began forming soon after, and that the earliest traces of stability appeared not in myth, but in mineral. The isotopes do not exaggerate, they do not speculate, they simply exist, decaying quietly in the dark, keeping time for anyone patient enough to ask. Imagine a planet that never slept. Around 3 billion years ago, the Earth was still a young and restless thing, its skin cracked with volcanoes and its breath thick with steam. The continents were not yet the broad, stable platforms we stand on today, but scattered volcanic rafts adrift on an ocean of molten mantle. The air above them shimmered with heat and metal, and the sky was stained with the faint orange of methane and haze. This was a world of fire and water, violence and calm in an uneasy balance. A time when the planet's crust was finally learning to hold itself together. The story of this era begins deep beneath our feet, in the convecting mantle. Heat still poured outward from Earth's interior, a remnant of its violent birth, driving constant motion. Entire plates of crust rose and sank like slow waves. When one fragment of crust pushed beneath another, the pressure melted rock into magma, which then welled upward to build new volcanic arcs. Through this endless cycle of creation and destruction, small islands of more buoyant rock began to survive longer than others. Over millions of years, these islands fused into the first stable continental nuclei, cratons. A craton is not just old rock. It is the planet's foundation stone. Each one is a core of iron-rich metamorphic rock, buried deep under younger sediments, so stable that it has resisted the reshaping of plate tectonics for billions of years. The 𝐓𝐈𝐌𝐄𝐒 in southern Africa, the Pilbara in Western Australia, the Slave in Canada. These are the literal ancestors of continents. To this day, diamonds form in their roots under pressures so great and timescales so long that the stones we mine now were born before oxygen filled the sky. The late Archean world was dominated by this slow building of permanence. Beneath volcanic arcs and rifting seas, the chemistry of the crust was changing. The rocks we see from that time, greenstone belts and tonalite trondhjemite granodiorite complexes, reveal a planet experimenting with stability. The earliest crust had been basaltic, thin and easily recycled by subduction. But these new granitic rocks were lighter, allowing them to float higher on the mantle and resist destruction. The continents, once fleeting, began to endure. Above the growing land masses, storms gathered daily in the dense atmosphere. The sun was fainter then, its light about 70% of what it is today, yet the greenhouse gases that blanketed the planet kept it warm enough for liquid water to persist. Lightning flashed constantly, feeding energy into a sky full of carbon dioxide, methane, and nitrogen. Rain fell through that chemical haze and hit newly formed rock, carving rivers that poured minerals into the sea. Each drop of water dissolved the planet a little, teaching the surface to cycle elements, the way a living body circulates blood. At the same time, deep within the oceans, life had begun to influence geology. Microbial mats spread across shallow seafloors, trapping sediments into layered structures called stromatolites. These were not just biological curiosities, they were factories of transformation. Within their slimy films, cyanobacteria drew energy from sunlight, splitting water molecules and releasing oxygen as waste. At first, that oxygen had nowhere to go. It reacted with dissolved iron in the oceans, forming rust-coloured minerals that settled as banded iron formations. These ancient iron layers, alternating dark and red, still mark the seafloors of that era. They are evidence of one of the most important chemical experiments in planetary history, the slow enrichment of the atmosphere with oxygen. By around 2¾ billion years ago, this process was gaining momentum. The oceans were slowly clearing of iron, and the air above them began to carry trace amounts of oxygen for the first time. It would still take hundreds of millions of years for this change to tip into a true oxygen crisis, but the groundwork was being laid. Life was already altering the atmosphere it depended on, and in doing so, it was rewriting the chemistry of the planet itself. The late Archean surface must have looked alien, yet familiar in form. There were mountains, rivers, rain, and oceans, but no grass, no soil, no green. The land was barren rock coated in thin films of microbial life. The colours would have been muted, dominated by grey volcanic stone, black lava, and rusty iron sediments. The oceans, rich in dissolved metals, may have shimmered green, or even purple under a dim orange sun. The air was heavy, with pressures and compositions that would choke us instantly. And yet, this world was stable in a way it had never been before. It was learning to keep records. The rock record from this time tells us more than just chemistry. It tells us about rhythm. Sedimentary cycles began to appear with predictable patterns, rivers laying down sands, tides leaving laminations, volcanic ash marking seasonal pulses. For the first time, Earth had a system of self-consistent layers, one event building neatly on another instead of being wiped away by molten upheaval. This consistency is what allowed geologists billions of years later to reconstruct what happened. It marked the transition from a chaotic recycling world to one capable of memory. Continental crust thickened. Weathering on land began to draw carbon dioxide out of the atmosphere, regulating temperature. Erosion fed nutrients into the oceans, supporting microbial colonies that in turn changed the composition of those same oceans. It was an elegant loop, one that hinted at the feedback systems that would later define climate and life. Even without vegetation, even without animals, the Earth had begun to behave like a single interconnected organism. Volcanism remained intense. Massive eruptions poured out basalt across vast provinces, sometimes covering areas larger than modern Europe. These eruptions released gases that would have balanced or countered the early oxygen being made in the seas. The battle between oxygen and volcanic gas was constant, a slow chemical war that shaped everything that followed. Each eruption also built mountains, and each mountain as it eroded exposed new minerals for weathering. The carbon cycle, still primitive, was beginning its long dialogue with life. If you could stand on one of those early continents, perhaps on the rim of the 𝐓𝐈𝐌𝐿𝐄𝐒 shield, you would see a skyline unlike any other. Towering volcanoes dominated the horizon, their summits glowing red at night. Rivers braided through rocky plains, carving canyons that filled with mist each morning. The air would carry the scent of sulphur and metal, and the roar of boiling springs would echo for miles. Yet somewhere in the quiet tide pools, microbial mats would be spreading, gluing grains of sand together into fragile domes that broke apart with each wave only to regrow again. It was a balance between destruction and persistence, and somehow life preferred it that way. By the time we reached the end of this era, around 2.5 billion years ago, the planet had grown quieter on the inside. The heat flow from the core had decreased, the crust thickened, and the first supercontinent-like assemblies may have begun to take shape. Some researchers believe fragments of these protocontinents were already drifting together, foreshadowing the later landmass known as Nuna or Columbia. If true, it would mean that by this point the Earth was entering a period of relative tectonic calm. The foundations for the continents we know were already in place, waiting for the next act. This was the calm before the erasure, the moment the planet stabilized enough to start keeping its deepest records, just before it would lose many of them forever. The rocks from this time form the bottom chapters of the story that later vanish in the Great Unconformity. They are the last coherent memories before the gap. They show a world alive with volcanic energy, wrapped in an atmosphere just beginning to shift, and covered in oceans where life had started to experiment with oxygen. Everything that happened afterward would build on this groundwork. It is humbling to think that the crust beneath our modern continents began its life in that fiery age. The stones in the walls of ancient temples, the grains of sand beneath modern seas, the iron in our blood, all trace their origin to this Archean laboratory of fire and ice. Every mountain today contains atoms that were once part of that molten crust, cooled, remelted, and reassembled countless times. The stability we now take for granted, the idea that a continent can last for billions of years, was an invention of this age. The late Archean was not a peaceful time, but it was a maturing one. The planet was finally learning balance. Too much heat and the crust would melt, too little, and the interior would freeze, halting tectonics. Somehow the Earth maintained just enough heat to keep its plates moving, its volcanoes venting and its oceans circulating. That delicate equilibrium is what made everything else possible. We know all this not from imagination, but from the rocks themselves. The isotopic signatures of ancient zircons, the layering of greenstone belts, and the ratios of rare earth elements tell us the temperatures, pressures, and compositions of the crust from billions of years ago. These are the only clues we have, and they are faint. The rocks have been metamorphosed and deformed, folded into mountains and buried deep within them. Yet their chemistry still carries the record of that time. Scientists continue to refine these reconstructions, comparing data from every craton on Earth to build a map of what the world looked like before the gap. We will never see that planet directly. No satellite could photograph it, no fossil could describe it. But through its chemistry, we can feel its presence, a hot, breathing world that balanced on the edge of change. It is the world that set the stage for everything that would follow, from the rise of oxygen to the eventual disappearance of time itself in the Great Unconformity. What kind of a world existed right before the record began to vanish? A world where continents found their footing, where life discovered light, and where the Earth, after ages of chaos, finally began to remember itself. Imagine this. The planet takes its first long, deep breath. Around 2.5 billion years ago, the continents that had once been mute slabs of rock began to react with the air above them. Rain fell, rivers ran, and for the first time the land began to pull gases from the atmosphere, changing the very chemistry of the sky. In a way, the continents had learned to breathe. The exhalations of volcanoes and the slow inhalation of the minerals became part of the same planetary rhythm, a feedback loop linking rock, ocean and air in one living exchange. This age marks what scientists call the Great Oxidation Event, a period when oxygen, once rare and fleeting, started to accumulate in the atmosphere. But oxygen did not simply appear overnight. It was coaxed into being by a series of slow, intertwined processes that began deep within the crust and extended outward to the farthest reaches of the air. The first part of this story happens where rainwater meets rock. When carbon dioxide dissolves in water, it forms a weak acid, carbonic acid. As that rainwater trickles through cracks in soils, it reacts with minerals like feldspar and pyroxene, breaking them down into clay, releasing ions such as calcium and magnesium into rivers. These ions eventually reach the oceans, where they combine with dissolved carbon dioxide to form carbonate minerals. In this simple chemical chain, something profound occurs. Carbon is taken from the atmosphere and locked away in stone. Weathering, the slow dissolution of continents, became the planet's way of balancing its own air supply. At the same time, life in the oceans was beginning to make use of sunlight on a massive scale. Cyanobacteria, the architects of the first oxygenic photosynthesis, had already been releasing oxygen as a byproduct for hundreds of millions of years, but the oxygen had nowhere to accumulate. It was immediately consumed by reduced materials, iron, sulfur, and volcanic gases. The oceans were full of dissolved iron that eagerly bonded with any available oxygen, forming rust-like minerals that settled to the seafloor as banded iron formations. Each layer of red and black was a record of a planet trying to decide how much oxygen it could tolerate. As continents stabilized and spread wider, chemical weathering accelerated. The new land surfaces exposed vast areas of fresh rock to the atmosphere. Rivers carried more nutrients into the seas, feeding microbial life that in turn released more oxygen. It was a feedback loop of extraordinary subtlety. Weathering drew down carbon dioxide, cooling the climate just enough to slow volcanic outgassing, while life added oxygen faster than the planet could remove it. At some threshold, some still poorly defined tipping point, oxygen began to accumulate faster than it could be consumed. The planet crossed a line, and the atmosphere changed forever. To picture this world, imagine a sky just beginning to turn blue. Before this time, the atmosphere would have been hazy with methane, giving the sky a pale orange tint. As oxygen levels rose, that haze burned away. Methane reacted with oxygen to form carbon dioxide and water vapour, clearing the air and revealing a truer light from the sun. The colour of the sky itself was a chemical response to breathing rock. Below, the oceans responded in kind. As oxygen seeped into surface waters, it began to oxidize iron and sulfur, turning the seas a reddish hue in places, then slowly clearing them as the metals precipitated out. The first oxygenated zones appeared near the coasts and spread outward. In the deeper basins, anoxic waters lingered for millions of years, creating chemical gradients that life would later exploit. Even today, scientists find ancient sediments that record these patchy redox boundaries, thin transitions between an oxygen-rich and oxygen-poor world. The rocks on land record their own version of this transformation. Before the rise of oxygen, many ancient sediments contained minerals that could not survive in its presence. Pyrite, uraninite, siderite. Once oxygen appeared, those minerals began to weather away on contact with the air. Their disappearance from the rock record is one of the strongest pieces of evidence for atmospheric change. Around this same time, red beds, sedimentary layers stained by iron oxides, begin to appear, signalling that the surface was finally rusting in earnest. The continents had become reactive lungs, taking in carbon dioxide and exhaling oxygen through an intricate dance of biology and geology. It is tempting to imagine this transition as a triumph of life, but it was also a crisis. The increase in oxygen was catastrophic for most anaerobic organisms, which had evolved in a world without it. Oxygen is a powerful oxidizer. It breaks chemical bonds, damages cells, and burns through organic molecules with ease. What was a waste product for some became a poison for others. Entire microbial ecosystems would have been forced to retreat into deeper sediments or oxygen-free niches. The Great Oxidation event was both creation and extinction, a turning point in the metabolism of the planet. Meanwhile, the crust beneath all this was not passive. Weathering, by removing carbon dioxide from the air, gradually cooled the climate. Cooler temperatures meant less volcanic activity, which in turn reduced the supply of gases like methane and hydrogen sulfide that had been consuming oxygen. It was an intricate balancing act, one that still defines our climate system today. If the weathering rate slowed, carbon dioxide would build up, warming the planet and intensifying rainfall, which would then speed up weathering again. These negative feedbacks are what make Earth's climate uniquely stable over geological time. In a sense, the continents were learning how to breathe rhythmically, exhaling carbon when the world froze, inhaling it when the world overheated. Chemical weathering also began to erase parts of the Earth's earlier geological memory. The same processes that regulate climate also consume rock. As oxygenated rain and rivers carved through Archean crust, they dissolved away minerals that had preserved the earliest records of the planet's formation. Much of the continental surface from before this time was chemically stripped, its upper layers transformed into clays and oxides that washed into the sea. Those sediments would later lithify into new rocks, younger and more stable, but they carried only chemical echoes of the world that came before. The Earth was rewriting its autobiography, one reaction at a time. Evidence for this planetary transformation comes from tiny isotopic clues. In sulfur, for example, the isotopic ratios before and after the Great Oxidation event changed dramatically. In an oxygen-poor atmosphere, ultraviolet light splits sulfur dioxide into distinct isotopic patterns that are preserved in rocks. Once oxygen levels rose, the ozone layer formed and blocked that light, ending the unique isotopic signatures. It is a line so sharp in the geochemical record that scientists can identify the very boundary of atmospheric change. Carbon isotopes tell a similar story, showing shifts in the balance between organic carbon burial and volcanic outgassing. The combined data paint a picture of a planet entering a new phase of self-regulation, a shift from chemical chaos to biological control. The rise of oxygen also transformed the crust itself. New types of minerals began to appear. Over 2,000 varieties formed only in oxygen-rich environments. Copper and uranium oxidized into colourful ores. Manganese formed new compounds. Even the colour palette of the Earth changed. Geologists sometimes call this the mineralogical explosion. It was the planet's version of biological diversification, an expansion of possible chemistry brought on by a single molecule. If you could stand on one of those early continents, the changes would not have been immediate or visible in a human sense. The air would still have been thin and harsh, and oxygen levels, though rising, remained a fraction of modern values. But over millions of years, the transformation would have been profound. Red dust would have settled across landscapes, rivers would have carved deeper channels through softening stone, and the horizon might have brightened as haze gave way to light. The sound of rain on rock would have been the planet's quiet breathing. What we call air today is the result of these feedbacks balancing over immense time. The continents did not plan to regulate the atmosphere. They simply interacted with it until equilibrium emerged. The chemistry of minerals, the metabolism of microbes, the circulation of oceans, all worked together in ways no single force controlled. This is perhaps the most humbling realization of all. The stability of the air we depend on is not the product of design but of long, slow conversation between rock and life. In the end, this was the era when the Earth began to act like a system, complex, reactive, and self-correcting. The processes that started then still govern our world now. When carbon dioxide rises today, it increases weathering. When it falls, the planet cools, and the cycle slows. The same reactions that once balanced volcanic gases now buffer human emissions, though not nearly fast enough for our impatient species. In the rocks, time has always been the moderator. We can think of the Great Oxidation event as a planetary awakening, but perhaps it was more like a long sigh, a slow adjustment between inside and outside, heat and light, water and air. It gave us the first stable continents, the first breathable atmosphere, and the first hint that a planet could keep itself alive. But it also came at a cost. The early crust was weathered away, and vast parts of the planet's memory dissolved into the sea. The continents learned to breathe, but in doing so, they also began to forget. Imagine a world stitched together from every piece of land that would one day drift apart. Around 1 billion years ago, all the continents we know, Africa, North America, South America, Antarctica, Australia and Asia, were welded into one colossal body called Rodinia. Its name means to give birth in Russian, a poetic choice for a continent that would eventually fall asleep beneath ice. then awaken as the fragmented world we live on now. But in this distant past, Rodinia was whole, immense, and silent, an ancient crust stretched across the equator, surrounded by a vast global ocean. To understand what it means to build a supercontinent, imagine the Earth as a restless machine. The planet's crust floats atop slow, swirling convection currents in the mantle, heat rising from below, spreading outward, then sinking again as it cools. These cycles drag continents together and tear them apart in rhythmic intervals lasting hundreds of millions of years. Rodinia was one of these moments of gathering, when the wandering continents that had drifted apart after an earlier union called Columbia found each other again. For a time, the Earth's surface calmed, its plates locked in a continental embrace that would last for hundreds of millions of years. The joining of Rodinia was not peaceful. It began with collisions. Ocean basins closed as continental plates moved toward one another, crumpling their edges into mountain ranges that dwarfed anything alive today. The Grenville orogeny, one of the greatest mountain-building events in Earth's history, stretched across what is now North America, forming peaks comparable in height to the modern Himalayas. To the south and west, the Kalahari and Congo cratons slammed into the Laurentian core, and what would one day become Australia fused to the whole along long belts of metamorphic rock. The impact zones of these collisions still survive as scars in the oldest rocks we can find, pressure-hardened minerals that tell us how violently the planet was assembling itself. When continents collide, their crust thickens, rises, and exposes deep rock to the surface. In Rodinia's case, that uplift exposed vast expanses of crystalline basement, ancient roots of continents that had not seen sunlight for billions of years. Over time, rain and wind began to wear them down, stripping away soil and sediment until the raw architecture of the planet was visible. The surface of Rodinia became a gallery of granite and metamorphic stone, rich in minerals but largely barren of the life. It was a place of erosion and stillness, a continent that seemed to hold its breath. While the mountains rose, the world around them changed in slower, quieter ways. The ocean circulation that had once wrapped around separate continents began to reorganize. The supercontinent acted as a massive heat sink, absorbing sunlight during the day and radiating it at night. This altered global climate patterns, though we cannot yet know exactly how. The vast interior of Rodinia likely experienced temperature extremes, with deserts and seasonal storms, while its coasts faced monsoon-like rainfall. River systems carried minerals from the highlands to the oceans, feeding chemical reactions that subtly shifted the balance of carbon and oxygen between air, land, and sea. Tectonics continued beneath this apparent calm. The weight of the mountains pressed down on the crust, causing the mantle below to flow and deform. As deep rocks metamorphosed, they released fluids that rose through cracks, depositing veins of copper, gold, and other metals. These slow alchemical processes built the ore deposits that would one day become resources for distant civilizations, though for now they remained sealed in the silent crust. The supercontinent was a laboratory of pressure and heat, a slow geochemical engine refining its own interior. Rodinia's geography remains uncertain. The evidence is fragmentary: zircon grains, paleomagnetic data, and matching belts of metamorphic rock scattered across modern continents. From these clues, geologists have reconstructed a probable layout. Laurentia, the ancient heart of North America, sat near the centre, while Australia and Antarctica nestled against its western edge. South America may have curved around its southern flank, and Siberia might have been attached to the north. But the map is not fixed. Scientists still argue about where each piece fit. In a way, our modern debates mirror the planet's own uncertainty during that time, a shifting experimental configuration that would not last. The slow drift of continents did not stop just because they had collided. Heat continued to build beneath the thick crust, trapped by the insulation of the supercontinent itself. Mantle plumes, giant columns of molten rock, began to rise from deep within the earth, weakening Rodinia's underbelly. These plumes erupted through the crust in great floods of basalt, cracking the surface and forming enormous volcanic provinces. Each eruption released gases that altered the atmosphere, while each fracture became a seed for future oceans. It is from these fissures that the next cycle of separation would begin. As the centuries of rock and erosion passed, Rodinia entered a long, slow slumber. The mountains that had risen so dramatically began to crumble. Rivers carried their sediments into shallow seas that pooled along continental margins. The land slowly flattened, smoothed by time, and for the first time in billions of years, the surface of the planet was dominated not by violent upheaval, but by long, quiet erosion. The supercontinent had stabilized, but at the cost of motion. It was like a single breath held for hundreds of millions of years. During this period of stillness, something subtle but profound was happening. The exposure of basement rocks, especially those rich in silicate minerals, increased the rate of chemical weathering. As rainwater reacted with these minerals, it pulled more carbon dioxide from the atmosphere, storing it in carbonate rocks on the seafloor. Over geological timescales, this process may have cooled the planet. The combination of stable continents and declining carbon dioxide set the stage for events that would come later. Global shifts in climate and ocean chemistry, whose fingerprints still shape the rock record. Though we will not yet speak of those consequences, the seeds of them were already germinating. Rodinia's long sleep was not total hibernation. Beneath the crust, the mantle churned. As heat accumulated, convection cells began to tear at the base of the supercontinent, forming rifts that would one day become new ocean basins. Along these growing cracks, magma intruded, forcing its way toward the surface. These early rift zones may have glowed at night with lava flows stretching for hundreds of kilometers, silent under the pale light of the ancient moon. It was tectonic tension building in slow motion, a countdown to disintegration. The breakup of Rodinia began perhaps around 800 million years ago. It started with subtle shifts, crustal thinning, subsidence, and the rise of great continental domes. Eventually parts of the supercontinent drifted apart, opening proto-oceans such as the Morovia and the Panthalassic. As the land masses separated, new coastlines appeared, and fresh rock was once again exposed to the atmosphere. The cycle of uplift and erosion restarted, feeding nutrients into the seas, altering the chemical balance of the oceans, and setting in motion feedbacks that would eventually change the planet forever. But for the long stretch of its existence, Rodinia represented an age of consolidation, the Earth's attempt to rest after aeons of instability. The forces that built it and the forces that tore it apart were the same, operating at scales beyond imagination. Each supercontinent cycle takes about 500 million years from assembly to breakup. In human terms, it is the heartbeat of the planet, slow, steady and powerful. We live in the aftermath of several such cycles, and the continents beneath our feet still carry the buried bones of those earlier unions. When we look at the cratons of modern continents, those deep ancient roots of granite and metamorphic rock, we are looking at the skeleton of Rodinia itself, the Canadian Shield, the Australian outback, the deserts of Namibia, and the mountains of Siberia all hold fragments of that ancient continent. Even now, their rocks align like puzzle pieces if you trace their magnetic signatures. The Earth may have forgotten many details of its past, but the magnetic minerals in those stones still remember the orientation of the planet's poles as they cooled. It is through that magnetism that scientists reconstruct the story of Rodinia's drift and dissolution. How do you erase a supercontinent? You do it slowly, invisibly, from within. You let its mountains crumble and its crust stretch until rifts widen into seas. You let the wind and rain polish its surface until all that remains are scattered shields of stone, each carrying a different memory of the same ancient whole. The erasure of Rodinia was not destruction, it was transformation. The pieces that broke away became the continents we know, but the process also exposed new rock, fresh surfaces that would one day weather, react, and participate in the next planetary cycle. Rodinia's long sleep, then, was the pause before renewal. It was the Earth's way of gathering energy for what would come next. A planet learning to change by forgetting. A surface preparing to be rewritten. The stability of this age laid the foundation for the upheavals to follow, for the glaciers, the floods, and the bursts of life that would someday fill the gap left behind. It is the quiet before the missing time, the breath drawn in before the silence that still divides the geological record. Imagine this. The world turns white. Not the gentle white of a winter morning, but a planetary whiteout, a frozen sphere drifting through space, its oceans sealed beneath kilometers of ice. Around 720 million years ago, Earth may have entered one of the most extreme states in its entire history. We call it Snowball Earth, though it might be more accurate to call it the planet's longest deep freeze. Ice crept from the poles toward the equator, glaciers ground across continents, and sunlight reflected off the frozen surface until the entire climate system locked into feedback. For millions of years, the world was encased in a silence of ice and pressure. To grasp the scale of what this means, imagine the entire surface of the planet as a single glacier. The Sturtian glaciation, which began around 720 million years ago, and the Marinoan glaciation, which followed later, are recorded in rocks on nearly every continent. We find glacial striations, parallel grooves carved by sliding ice, in places that once sat near the equator. We find dropstones, lone boulders carried by icebergs and dropped into fine sediment as the ice melted, preserved in what were once tropical seas. These clues tell us that the freezing was global, not local. The ice was not content with mountains. It reached the beaches, the forests that would one day exist, and the equatorial plains. But glaciers are not static things. Even when the planet is frozen, they move. The weight of ice thick enough to crush mountain ranges forces it to flow outward under its own pressure. As it moves, it scrapes against the rock beneath, picking up debris, grinding it into dust and polishing the surface into smooth plains of stone. This process, glacial abrasion, is one of nature's most efficient tools for erasing. Under a kilometre of ice, even granite yields its minerals scratched and smeared into fine sediment. If the Great Unconformity was indeed formed by this ancient global glaciation, then the missing billion years of rock might have been ground away, grain by grain, under the relentless crawl of frozen water. At that time, the continents were gathered mostly near the equator, remnants of Rodinia now drifting apart. The geography of that arrangement amplified the freeze, with most land in the tropics weathering drew down carbon dioxide rapidly, pulling greenhouse gases from the air just when volcanic output slowed. Less carbon dioxide meant less heat trapped by the atmosphere, which in turn allowed ice to spread farther. The more the ice spread, the more sunlight it reflected, further cooling the planet in a runaway loop. Once the oceans froze over, the system became nearly inescapable. Geophysical models suggest that ocean ice may have been hundreds of meters thick, with glaciers extending far into shallow seas. Beneath the ice, currents still moved slowly, and volcanism continued to release heat and gas from the seafloor. But above, the surface world lay dormant, encased in silence. Temperatures could have fallen below -50 degrees Celsius at the surface, and the air would have been dry, thin, and almost still. Winds would have carved the ice into vast dunes, and the continents beneath would have been hidden entirely from view. Yet even in this apparent stillness, immense geological change was underway. The movement of ice across the continents acted like an enormous sander, levelling mountains and stripping away soil. Where ancient metamorphic rocks once stood, glaciers scraped them bare, leaving behind striated pavements and broad, polished shields. These surfaces would later serve as the foundation for new sedimentary layers after the ice melted. The grinding also released vast amounts of ground-up mineral dust, fine rock flour that was carried by subglacial streams and deposited across continental shelves. Much of this material would later lithify into diamictites, mixed deposits of boulders and clay, that remain one of the key signatures of this period. Some of the evidence for this global glaciation comes from the peculiar layering of rocks. Across many continents, we find thick sequences of glacial tillites overlain abruptly by carbonates, rocks formed in warm, shallow seas. This sharp transition suggests that after the deep freeze ended, the climate rebounded dramatically. But during the freeze itself, the erosional power of the ice was immense. In places like North America, Australia, and Namibia, the pre-glacial basement rocks show widespread planation. Flat, smooth surfaces that extend for hundreds of kilometres. It is difficult to explain such global uniformity by normal weathering or local glaciation alone. Only a planetary-scale ice sheet could produce that kind of mechanical precision. The physics of glaciers explain how. The base of a large glacier is not entirely frozen. Pressure from the overlying ice lowers the melting point of water, creating a thin film of meltwater that lubricates the interface between ice and rock. This allows the glacier to slide, carrying embedded debris like sandpaper across the surface. The deeper the ice, the greater the pressure, and the more efficient the erosion. Over millions of years, this process can strip kilometres of crust, transporting the material downslope and depositing it far from its source. Beneath a global ice sheet, the continents themselves were reshaped. Mountain routes truncated, valleys deepened, and entire landscapes reset. Geologists studying ancient shield regions today often find that the uppermost layers of Precambrian rock have been removed almost uniformly, leaving behind exposed granitic basement. The Canadian Shield, for example, preserves vast areas of this polished stone, its surface dotted with glacial grooves that align in consistent directions. Similar patterns appear in Africa, South America, and Australia. When we compare these observations across continents, we see the outline of a shared event, an episode of planetary-scale erosion powerful enough to strip the Earth's crust down to its crystalline foundations. How could such a frozen world eventually thaw? The answer, as best we can tell, lies in the planet's internal persistence. Even during the deepest freeze, volcanoes never stopped erupting. Beneath the ice, carbon dioxide continued to accumulate in the atmosphere, because weathering, one of the main sinks of carbon, had nearly ceased. With the surface sealed in ice, there was no rain to pull carbon dioxide out of the air. Over millions of years, volcanic gases built up until the greenhouse effect grew strong enough to break the cycle. When the ice finally melted, the transformation would have been sudden. Oceans refilling, rivers cutting new channels, coastlines reappearing. But in that long frozen interval, the stage was set for one of the greatest erosional events in history. The snowball Earth hypothesis remains one of the most debated topics in geoscience. Some researchers propose that the planet was not completely frozen, that belts of open water, so-called slushball conditions, persisted near the equator. Others argue for multiple glaciations of varying intensity. What unites these interpretations is the shared evidence of enormous glaciers operating at sea level, their fingerprints etched into rocks on every continent. Whether the Earth was fully encased or partially open, the erosional consequences were immense. To imagine this world in motion, picture a slow ballet of ice sheets creeping across Rodinia's remnants. The supercontinent was already fragmenting, but the ice bound its pieces together again temporarily, wrapping the drifting landmasses in a shared mantle of cold. Where mountain chains had once risen, glaciers poured through valleys, carving U-shaped troughs that would later become fjords and basins. Where lowlands stretched to the horizon, ice polished them flat. Every movement was a form of forgetting. The ancient weathered surfaces, the soils and sediments that recorded earlier climates were obliterated. In the modern world, we can watch a miniature version of this process in Greenland or Antarctica. Glacial ice there grinds down bedrock at measurable rates, producing fine silt that clouds the meltwater flowing beneath. Scale that process up to a global level and stretch it over tens of millions of years, and the power becomes unfathomable. The deep freeze may have been the planet's most efficient eraser. When the ice finally withdrew, it left behind a world scoured clean. The continents that emerged were stripped to their cores, bare, eroded platforms of crystalline rock ready to receive new sediments. These surfaces, exposed and planned by ice, may be the ones we now see preserved beneath the Great Unconformity. They are the literal contact points between deep time and what came after. If glaciers did carve them, then the missing billion years of Earth's record might not be lost by accident, but by the deliberate physics of ice, pressure, and time. It is difficult to picture such stillness, yet such violence coexisting. A world that seemed asleep yet was furiously reshaping itself from beneath. Perhaps that is the paradox of deep time. Destruction and renewal are always the same motion viewed from different distances. The snowball Earth events remind us that even at its coldest, the planet was alive in the geological sense. Still moving, still cycling, still sculpting its future. We will never know the exact view from under that ancient ice, but we can walk on its memory. The polished stone floors of our oldest continents, the grooves carved into bedrock, the flattened surfaces that serve as the foundation for all later sediments, these are the fossils of glaciers themselves. They tell us that the Earth once wore a mantle of white thick enough to grind mountains into dust, to erase entire epochs, and to leave behind only a smooth silence in the stone. Imagine this. The ice finally begins to melt. After tens of millions of years of stillness, rivers of liquid water rush back across the surface of the world, carving new valleys where glaciers once stood. The continents that had been planned down to their bare foundations now crumble under the return of warmth. As the great frozen sheets retreat, they release torrents that roar across the scarred landscape, grinding ancient stone into dust and carrying it toward the newly thawed oceans. The planet exhales, but its breath is heavy with minerals. In that instant of planetary thaw, the chemistry of the ocean changes forever. When we talk about the Great Unconformity, we often picture missing rock. But what we rarely imagine is what all that rock became. The kilometres of crust that glaciers and weather stripped away did not simply vanish. They dissolved, eroded, and drifted as ions into the sea. Every atom removed from the continents had to go somewhere. The ocean, as always, was the final archive. Geochemists studying the aftermath of the snowball Earth periods find unmistakable signals in ancient sediments, anomalies in isotopes of carbon, strontium, and sulfur that tell the story of massive continental alteration. As the ice melted, intense weathering released enormous quantities of calcium, magnesium, and silica into seawater. The balance of the planet's chemistry shifted. Carbon dioxide, which had built up in the atmosphere during the freeze, reacted with the newly exposed rock to form carbonates, neutralizing acidity and drawing vast amounts of carbon into stone. This dance between atmosphere, land, and sea left chemical fingerprints still visible today. Picture the coastline of that thawing world. Glacial rivers, swollen with sediment, pour milky torrents into shallow seas. Their waters are opaque with dissolved minerals, bicarbonates from carbonic acid reacting with silicate rocks, calcium ions from crushed limestone, and iron from ground-down crust. These rivers are not just carrying the memory of the glaciers, they're carrying the memory of the billion years those glaciers erased. Each particle and ion is a chemical echo of vanished continents. As these materials reach the oceans, they begin to transform them. Calcium and bicarbonate combine to form calcium carbonate, precipitating as white mud that settles onto the seafloor. These layers are now preserved in what geologists call cap carbonates, distinctive limestone sequences that rest directly atop glacial deposits worldwide. Their abrupt appearance suggests a rapid influx of dissolved anions, an ocean suddenly supersaturated with carbonates. When the ice retreated, the seas fizzed with the chemical consequences of erosion. Silica too entered the ocean in enormous quantities. The grinding of continental crust released silicon dioxide into rivers, and without the biological filters that dominate later oceans, much of it remained in solution. Ancient cherts and silicious rocks from this time record this excess. The ocean was a chemical laboratory, flooded with the raw elements of crustal decay, and as the seas mixed and stabilized, these dissolved materials began to alter the isotopic signatures of seawater itself. In the isotopic record, this period appears as a series of sharp excursions, abrupt shifts in the ratios of carbon and strontium isotopes preserved in marine carbonates. These deviations mark a world struggling to re-equilibrate after its long freeze. The massive release of rock-derived ions altered the ratio of radiogenic strontium from continental crust, relative to mantle-derived sources, leaving a distinct signal that geologists can trace through time. It tells us that the Earth's surface had been stripped, that weathering had intensified to an almost unimaginable degree, and that the planet's geochemical cycles were running in overdrive. There is a poetic symmetry in this. The very act of forgetting, of eroding and erasing, enriched the oceans with the materials that would later enable memory to return. The Great Unconformity is not just a missing layer. It is the chemical prelude to renewal. The stripped continents bled their minerals into the sea, rewriting the ocean's composition in ways that would persist for hundreds of millions of years. The volume of this transfer is staggering to imagine. During the post-glacial melt, chemical weathering rates may have increased tenfold compared to normal conditions. Vast regions of newly exposed rock reacted simultaneously with acidic meltwater, releasing elements into circulation. If we could have observed it, the rivers would have run chalky white, and the shallow seas would have been blanketed with carbonate precipitation. The air itself would have shimmered with the reaction between carbon dioxide and rock as the planet adjusted its chemistry toward balance. This massive continental input did not just alter carbonates, it changed the salinity and alkalinity of the oceans. With so much calcium and magnesium entering the water, the buffering capacity of the sea increased, stabilizing pH levels. Silica concentrations rose, possibly creating conditions for the eventual appearance of siliceous skeletons in later life forms, though that story lies beyond this chapter. For now, it is enough to know that the ocean became chemically rich, a soup not of biology, but of geology. At the same time, the influx of nutrients such as phosphorus and iron may have fertilized the surface waters. Erosion exposed fresh minerals that readily released these elements when they met oxygenated water. The ocean's chemistry became more dynamic, with redox reactions cycling between dissolved iron and oxygen, forming banded mineral deposits in shallow shelves. These processes set the stage for a new kind of planet, one where the sea itself became a reactive participant in Earth's cycles, not just a passive basin. One of the enduring mysteries of this time is how these global geochemical changes connect to the Great Unconformity itself. The surfaces that were eroded flat by glaciers now lay beneath oceans enriched by the very elements those glaciers had carried away. In some places, the ancient crystalline basement rocks became the foundation for thick new layers of marine sediment, sandstones, shales, and carbonates deposited directly atop the polished stones of deep time. The chemical interaction between seawater and these freshly exposed rocks altered their uppermost millimeters, forming thin, weathering rinds that geologists can still detect today. In a way, the ocean left its signature on the rocks just as the rocks had altered the ocean. If we think of the Earth as a memory system, this was the chemical equivalent of amnesia followed by rewriting. The glaciers had wiped the slate clean, but the flood that followed inscribed new information onto it, information written not in fossils or structures, but in isotopes and dissolved ions. The chemistry of the ocean is a living archive, and during this period it recorded one of the most extreme transformations in planetary history. The isotopic evidence for this transformation is found in rocks on every continent. In Namibia, Australia, China, and North America, carbonate layers from this time display carbon isotope ratios that swing dramatically between positive and negative values. These variations likely reflect massive imbalances in the global carbon cycle, periods of rapid burial of carbonate minerals followed by oxidation of organic carbon. The strontium isotope ratios show a simultaneous spike, marking a surge of continental weathering. Together, these geochemical signals form a fingerprint of recovery, the planet thawing, dissolving, and reassembling itself. Even the deep ocean felt the effects. As the upper layers became enriched with dissolved ions, mixing currents carried these changes downward. Hydrothermal systems at mid-ocean ridges responded in turn, precipitating new minerals and altering the chemistry of ocean crust. In essence, the entire Earth system, from the highest mountain to the deepest trench, was chemically reset. The boundary between before and after is not marked by fossils or rock types alone, but by a global shift in the isotopic composition of seawater. And yet, for all our data, there are gaps in our understanding. We can measure the chemical traces but not fully reconstruct the mechanisms. How quickly did the oceans absorb the outflow of the continents? How long did the imbalance last? Was the weathering concentrated along certain margins, or was it evenly global? Each rock we study answers one question and opens three more. What we do know is that the chemistry of the oceans after the snowball Earth glaciations was nothing like what came before. The planet's deep freeze had acted as a pause, and when it ended, the hydrological and geochemical engines restarted with unprecedented force. The oceans became reactive, overcharged with ions, shimmering with new mineral equilibria. The surface of the Earth was, for a geological instant, chemically alive in a way it had never been before. We tend to think of erosion as loss, but sometimes loss is the precondition for transformation. The Great Unconformity and the oceanic anomalies that followed are two sides of the same event, one on land, one in the sea. The continents forgot their upper layers, and the oceans inherited their memory. The chemistry of forgetting, it turns out, is not silence at all, but reaction. It is the sound of a planet reorganizing its atoms, rearranging its balance sheets, and preparing, unknowingly, for the next chapter of its long experiment with time. In the deep time that followed, much of this buried material was drawn downward into subduction zones. Oceanic plates carrying continental debris were pushed beneath other plates, melting into magma and re-emerging as volcanic arcs. Some of the oldest granites on modern continents may contain elements recycled from this erosion pulse. Through isotope analysis, we can trace the movement of certain elements, neodymium, strontium, lead, and see that their ratios changed dramatically around this period. The crust was rejuvenating itself chemically, drawing from its own destroyed parts. So when we speak of the Great Unconformity as a gap, it's not a hole in the planet's record, it's a redistribution. What once formed the highlands of Rodinia now lies crushed beneath Gondwana. The stones that vanished from one part of the Earth became the foundations of another. Even the deep ocean sediments, eventually subducted into the mantle, are not truly lost. They re-emerge in volcanic rocks and granite intrusions, altered but traceable through their isotopic lineage. We can see evidence of this in the timing of metamorphic belts that form after the Neoproterozoic. Around 600 million years ago, as the Earth warmed and continents reorganized, many of these deep basins were caught in collisions during the assembly of Gondwana. The sediments eroded from Rodinia's ruins were now being crumpled, melted, and welded into new crust. The erasure of one world directly built the next. The planet is efficient like that. It forgets by rearranging. Another part of this mystery lies in the way sediment traps evolve over time. When glaciers retreat and sea level rises, erosion temporarily slows, but sedimentation accelerates in the flooded margins. During the late Neoproterozoic, fluctuating sea levels repeatedly flooded continental interiors, depositing broad sheets of sand and mud over the polished surfaces of the Unconformity. These cycles sealed the record of erosion under new blankets of deposition. In that sense, the Great Unconformity marks not just what was lost, but also the transition between two great geological rhythms, one of removal, one of renewal. The chemistry of the oceans, altered by the influx of continental ions, played a role in locking away much of this material. The calcium and carbonate that flooded the seas contributed to rapid limestone formation, which in turn trapped large quantities of eroded elements in sedimentary rock. Later, these carbonates would be buried and metamorphosed, recycling their contents into the deep crust. The billion years that vanished may well be dispersed across countless rocks, each holding a fraction of the erased surface in chemical disguise. The truth is that Earth never throws anything away. It repurposes. The same atoms that once formed the upper crust of Rodinia may now sit within a granite mountain in Canada, a sandstone ridge in Namibia, or a vein of quartz deep beneath the ocean floor. The Great Unconformity is therefore not an empty silence, but a reorganization of form. What we see as absence is really transformation. Solid rock turned to sediment. Sediment turned to stone again. Geologists today can even approximate how fast this recycling occurred by comparing the volume of eroded material with known sedimentation rates. The balance suggests that during this time, erosion and deposition nearly cancelled each other out on a global scale. The continents shed their weight while the oceans gathered it, keeping the planet's overall crustal mass relatively constant. The missing billion years are not gone. They have simply changed their address. It's humbling to think that the stones beneath our feet were once mountain summits, ground down and reassembled, passing through cycles older than any lineage of life. The Great Unconformity may look like a void, but it is really the planet's memory in motion. Every eroded particle became part of a larger geological story, one where disappearance and creation are indistinguishable. So, if those lost rocks didn't just vanish, where are they now? They are everywhere. They lie deep beneath the continents in metamorphic roots. They line the floors of ancient basins now hidden under newer strata. They circulate within the crust as recycled magma, their isotopic ghosts still detectable to the instruments of modern science. The Great Unconformity was never a deletion. It was an act of redistribution. When we trace the story of the missing billion years, what we really find is continuity. The rock that vanished from one surface reappeared as sediment somewhere else. Time in geology isn't erased. It's rearranged, rewritten, and recast in new materials. The Earth doesn't lose its memory. It simply stores it in different forms, waiting for us to find the connections again. Imagine this. You're standing on rock that once sat miles above its current place in time. Everything beneath your feet, every grain, every crystal, was once part of mountains long gone. The paradox of the Great Unconformity isn't just what's missing from the record, it's that the missing parts didn't vanish. They moved. They were carried away by rivers, buried under oceans, compacted, cooked, and folded into new layers of crust. Somewhere, far below and far away, the billion years we lost are still here, just no longer in the form we expect. After the great glaciations thawed and the continents began to crumble, erosion accelerated on a planetary scale. The glaciers had shaved the continents down to clean, crystalline stone, exposing fresh rock to the atmosphere. When the ice melted, rain fell on a landscape that was chemically raw. The newly exposed minerals reacted eagerly with water and carbon dioxide, breaking apart into ions and sediment. Rivers surged with silt, carrying the planet's memory downhill. The erosion rates we can model for this time are astonishing, orders of magnitude higher than modern ones. In less than 100 million years, entire mountain ranges were reduced to grains. But erosion, no matter how intense, is only half the story. The other half is burial. All that sediment had to go somewhere. As rivers poured into the seas, they built immense deltas and underwater fans, systems so large they rival the size of continents. The material stripped from the ancient crust filled deep basins along continental margins. Some of these basins formed as Rodinia broke apart, others at the edges of the newly assembling supercontinent Gondwana. Sediments flowed into them continuously, creating vast wedges of sand, silt and mud that would later be buried under kilometres of newer layers. We can still find these deposits today. In places like the Grand Canyon, the Flathead sandstone and its equivalents in other continents rest directly atop the polished basement rocks that mark the Great Unconformity. Those sandstones are the first geological whispers of return, the moment erosion turned into accumulation again. Yet for every layer that survived, countless others were carried deeper and deeper into the slow, recycling system of metamorphism. The lost billion years didn't disappear. They were compacted, heated, and transfigured into the rocks that now lie deep beneath mountain belts. When geologists trace the isotopic composition of ancient sediments, they can sometimes identify their origins. The chemical fingerprints of zircons, the tiny durable crystals that survive even when their host rocks are destroyed, show that many grains found in younger sandstones are much older than the rocks they're part of. Some zircons in Cambrian and Ordovician sediments date back more than 3 billion years. That means they were eroded from ancient continental crust, transported and redeposited multiple times. These tiny minerals are like memory fragments drifting through time, surviving cycles of destruction that erase everything else. To find where the billion years went, we have to follow these clues. Modern erosion models and sediment budgets give us rough numbers. During intense post-glacial erosion, as much as 100 metres of continental crust may have been removed on average. Across all land masses, that could represent tens of millions of cubic kilometres of rock, enough to fill the deep ocean basins many times over. The ocean floor, though constantly recycled by plate tectonics, briefly became the resting place of this vanished material. The sediment piled up in continental margins, thickening the crust along the edges of plates. These deposits acted as thermal blankets, insulating the mantle and influencing later tectonic behaviour. Deep in those basins, pressure and temperature worked their slow magic. At depths of several kilometres, sandstones turned into quartzite, shales into slate and schist, carbonates into marble. The original textures of sediment disappeared, replaced by minerals that recorded only pressure and heat. When later mountain building events lifted these rocks again, they emerged transformed. In a sense, the billion years we think of as missing are simply hidden behind new faces. The ancient world isn't gone, it's metamorphosed. One of the more fascinating aspects of this recycling is how interconnected it is. The sediments eroded during this time likely contributed to the formation of many of the world's oldest passive margins, regions where continents transition quietly into ocean basins. The weight of accumulating sediment caused the crust to sink, creating space for more to collect. This feedback maintained high erosion rates for millions of years, a self-sustaining system of removal and deposition. In some basins, the sedimentary sequences reached thicknesses of 10 kilometers or more, recording continuous deposition that swallowed the remnants of earlier continents. Imagine this. You pick up a crystal older than the mountains it lies within, polish it, and measure the atoms inside, only to find that its memory has fractured. One part says it was born 3 billion years ago. Another insists only 600 million. The same grain, two conflicting truths. Somewhere inside that mineral, time has glitched. This is not a laboratory error. It's one of the most perplexing features of deep time. Rocks that seem to remember and forget simultaneously. When geologists first began dating zircons using uranium-lead systems, they expected precision. Uranium decays to lead in predictable ways, with half-lives so long they make atomic clocks out of the Earth's minerals. But as instruments improved, so did the contradictions. Some zircons told coherent stories, old ages with consistent isotope ratios, while others refused to line up. The clocks were discordant, the timelines bent. It was as though the minerals had been through something that scrambled their sense of chronology. To understand why, we have to remember how a zircon works. Zircon, or zirconium silicate, forms in magma as it cools. It's dense, tough, and remarkably resistant to chemical weathering. Inside, uranium atoms replace zirconium in the crystal lattice, while lead, normally incompatible with the mineral, becomes trapped as uranium decays. Over time, the ratio of uranium to lead tells us how long it has been since the crystal formed. But there's a catch. These isotopic clocks are not invincible. Heat, pressure, and fluids can disturb them. When a rock undergoes metamorphism, when it's buried deep enough to partially melt or recrystallize, the zircon lattice can be damaged. Uranium and lead atoms can migrate, resetting parts of the clock while others keep ticking. The result is discordance, mixed ages that don't match, memories rewritten in half-truths. In the context of the Great Unconformity, these discordant zircons matter deeply. Across the world, basement rocks just beneath that boundary often yield radiometric ages that are older than expected, but partially reset around the same window of time, between roughly 600 and 540 million years ago. It's as if a global pulse of heat and pressure swept through the crust, partially erasing the isotopic record. Some scientists interpret this as the metamorphic echo of the same forces that created the unconformity itself: massive erosion, burial, and tectonic rearrangement during the breakup of Rodinia and the assembly of Gondwana. Others see it as a thermal overprint from deep burial under newly deposited sediments. Either way, the clocks glitched not by chance, but by process. The behaviour of uranium-lead systems is well understood in principle. Uranium has two isotopes that decay to lead at different rates: uranium-238 to lead-206 and uranium-235 to lead-207. Each decay series is independent, and comparing them allows geologists to cross-check results. When plotted on a Concordia diagram, a curve representing perfect agreement, zircon data that have remained closed systems fall directly on the line. But when lead has been lost, or uranium redistributed, the data points fall off the curve. The degree of discordance tells us how much the system was disturbed and when. Using this method, scientists can not only estimate the original crystallization age, but also the timing of the event that reset it. Zircons, in other words, are not broken clocks, they're clocks that record trauma. Imagine a zircon as a small, transparent diary. The outer edges might have been rewritten during a metamorphic episode, while the core still holds the memory of its birth. Using tools like ion microprobes and laser ablation mass spectrometry, researchers can now read these diaries zone by zone, analysing the isotopic composition at microscopic scales. Under a cathodoluminescence microscope, the interior glows in concentric rings, growth zones like tree rings, each representing a phase of the mineral's life. Some are clean and bright, others are cloudy, scarred by radiation damage or fluid infiltration. Each zone carries a different isotopic ratio, a separate timestamp in the mineral's biography. What makes this fascinating is that the discordance is not random. Across continents, From North America to India, from Australia to Africa, the same pattern appears. Zircons from the deep crust show evidence of thermal resetting around the same Neoproterozoic to early Cambrian window. It's as if the planet experienced a synchronized pulse of metamorphism and fluid movement. This synchronization fits neatly with what we know about the tectonic and erosional events surrounding the Great Unconformity. Crust stripped bare by glaciers, covered by new sediments, then heated by burial and tectonic stress as new mountain chains formed. The result was a kind of geological amnesia, an isotopic fog that swept across the world's mineral archives. When geologists describe these processes, they often use the language of forgetting. A zircon that has lost lead is said to have been reset. A rock that has been metamorphosed is described as having its previous history erased. The metaphors are apt because the process is so literal. The isotopic systems that once stored the memory of formation lose coherence. Lead atoms, mobilized by heat or fluid, diffuse out of the crystal or migrate along fractures. The isotopic ratios that once told time now tell of disturbance. The mineral remains, but its story blurs. This kind of partial resetting complicates our understanding of the crust's evolution. In places like the Rocky Mountains or the Canadian Shield, basement rocks yield complex patterns of discordant ages, with multiple generations of zircon overgrowths, recording successive pulses of heating and deformation. Some of these may correspond as deep burial under kilometres of sediment after glaciation, others to continental collisions during Gondwana's assembly. The data weave together like overlapping memories, some clear, others fragmented. Reading them is less like opening a clock and more like deciphering a palimpsest. To put numbers to this phenomenon, scientists model lead diffusion in zircon as a function of temperature and time. At around 900 degrees Celsius, zircon will completely reset within days. At 600 degrees, it might take millions of years. Even at lower temperatures, radiation damage can create pathways for diffusion, allowing selective loss of lead without melting. The complexity of these variables means that no two zircons record time in quite the same way. The discordance is not a flaw, it is the mineral's autobiography of stress. In practical terms, this means that the Great Unconformity represents not just a missing physical record, but a disturbed chronological one. Even the minerals that survived the erosion physically were rewritten chemically. The crust didn't just lose rock, it lost coherence in its isotopic memory. The billion years of missing surface may have taken much of the isotopic context with it. When we try to date the rocks that remain, we are reading a diary that's been soaked, dried, and annotated centuries later. It's worth noting that zircon is one of the most durable minerals on Earth. If even zircon can forget, that tells us how intense the Neoproterozoic upheaval must have been. Other minerals, monazite, titanite, apatite, are far more susceptible to resetting. Together, these mineral systems give us overlapping perspectives on the same events. In many cases, they all show disturbance around the same window of time. It's a consistent global whisper of metamorphism, hinting at a shared cause that left no single origin untouched. Scientists still debate the full implications. Does the widespread resetting of radiometric systems indicate a truly global thermal event, or multiple regional ones coinciding by chance? Could the heat from thick sediment burial alone be enough, or did deeper tectonic forces contribute? These are open questions, but what is clear is that the rocks beneath the Great Unconformity have all been through something powerful enough to confuse time itself. There's a kind of poetry in that. The Great Unconformity is not just a physical boundary between old and new rocks. It's a boundary between clarity and confusion, between memory and its absence. The zircons sitting at that interface are survivors of both creation and erasure. They remind us that time in geology is not a perfect continuum, but a system subject to its own failures. When we hold one of those tiny crystals and see two contradictory ages inside, we are not seeing an error. We are seeing the fingerprints of deep time's own complexity. The Earth, it seems, keeps time the way a living thing does, imperfectly, through scars and renewals. The isotopic clocks we rely on are precise in theory but human in practice, capable of remembering, forgetting, and misremembering all at once. The discordance of the zircons is not a failure of measurement, it is the evidence of experience. So when we say the Great Unconformity marks a gap of 1 billion years, we are speaking not only of missing rock, but of a planet whose clocks were once collectively reset. The surface was scoured, the sediments buried, and the minerals themselves made to forget. Time was not destroyed, only rearranged. What we call a glitch is, in truth, the natural rhythm of a planet rewriting its past. Imagine this. After 1 billion years of silence, the world takes a breath. The ice has melted, the continents have bled their minerals into the sea, and the atmosphere hums with a new chemical balance. The rocks that once lay buried beneath kilometres of glacier now bask in warm sunlight. The oceans, once strangled beneath ice, begin to stir. In the grand rhythm of deep time, this is the moment when the Earth seems to wake up. Around 540 million years ago, the story of the Great Unconformity turned from erasure to creation. For nearly 1 billion years, vast portions of the crust had been planned down by ice, wind, and weather. When the glaciers finally retreated, they left behind oceans filled with dissolved nutrients, calcium, phosphorus, silica, iron, each a key ingredient for life. The surface that had been stripped of memory now became fertile again, not in soil but in chemistry. The planet, in its most literal sense, rebooted. Geochemists studying ancient marine deposits see this reboot written in isotopes. In carbonate rocks just above the Great Unconformity, ratios of carbon, sulfur, and strontium suddenly shift. These chemical fingerprints record oceans enriched with oxygen and minerals at levels never seen before. The rise in calcium and sulfate concentrations corresponds to more weathering of the continents, while iron and phosphorus washed in from the newly exposed crust. Together they formed a perfect storm of habitability. Oceans that could sustain complex metabolisms and oxygen, that could support multicellular respiration. It was not a coincidence that, right above this boundary, the fossil record erupts. To understand how this happened, picture the planet's surface after the long glacial cycles. The continents were scoured down to their crystalline roots, stripped of old sedimentary blankets that once insulated them. Fresh rock was exposed. Granite, basalt, ancient crustal material rich in reactive minerals. Rain, rivers, and wind began to attack these surfaces relentlessly. Every drop of water that ran to the sea carried a little of that rock's chemistry with it. Calcium ions from feldspars, bicarbonate from carbon dioxide reacting with silicate, phosphate from apatite, iron from weathered oxides. Each river became a chemical artery connecting the continents to the sea. In the shallow margins of those seas, new sediments began to accumulate. These were not the coarse sandstones of a dead world, but carbonates and shales teeming with the first traces of biological processing. Microbial mats colonized coastal flats, photosynthetic communities thrived, and oxygen levels, measured indirectly through sulfur isotope fractionation, began to rise. For billions of years, oxygen had remained scarce, a trace gas in a reducing atmosphere. Now, with continental weathering liberating nutrients, and the ocean stirring with productivity, oxygen began to build faster than it could be consumed. The transformation was planetary. Sedimentary records show that by the early Cambrian period, the ocean's redox structure had shifted dramatically. What had once been stratified into anoxic depths and oxygen-poor shallows became increasingly ventilated. This ventilation coincides precisely with the deposition of widespread shallow marine sandstones and carbonates resting atop the Great Unconformity. Those sediments, the tapetes, sandstone of the Grand Canyon, the Flathead Sandstone of the Rockies, the Chapel Island Formation of Newfoundland, mark the transgression of seas across the newly stabilized continents. Each one represents a global flooding event, an ocean reclaiming its eroded stage. As the seas advanced, they carried with them not only water, but chemistry. Dissolved ions from the continents that altered the ocean's buffering systems. Increased calcium and magnesium concentrations changed the way carbon dioxide interacted with seawater, helping stabilize pH and allowing carbonate skeletons to form more easily. In essence, the same chemical weathering that erased 1 billion years of rock had created the conditions for shells to exist. The crust had forgotten, but life began to remember. The Cambrian explosion, though biological in expression, was geochemical at its root. For life to diversify so dramatically, it needed energy, nutrients, and oxygen, all of which were delivered by the Earth's recovery from its long freeze. The sediments deposited after the Great Unconformity show strong evidence of increased phosphorus cycling, a nutrient that drives biological productivity. More photosynthesis meant more oxygen, and more oxygen meant new ecological niches for animals capable of using it efficiently. By altering its surface through erosion and chemical flux, the Earth unintentionally engineered its own awakening. It is difficult to overstate the magnitude of this shift. For nearly 4 billion years, the planet's biosphere had been microbial, simple, patient, and slow. Then, within a geological instant, ecosystems began building themselves in 3 dimensions. Sediment became scaffold, oxygen became fuel, and calcium became architecture. The rock record above the Great Unconformity does not just mark a return to deposition. It marks the dawn of visible life. Geologists often describe this transition in terms of feedbacks. As oxygen rose, it oxidized iron in the oceans, removing a major sink for reduced gases. This allowed more oxygen to accumulate, which in turn fueled further biological expansion. Weathering of fresh continental crust drew down carbon dioxide, cooling the climate to more stable conditions. Volcanism released trace metals that catalyzed new biochemical pathways. In this web of interactions, the planet effectively reset its own thermostat and composition. It was not just recovering from catastrophe, it was reorganizing itself into a new equilibrium. And yet, we must be careful not to simplify the story into cause and effect. The relationship between the Great Unconformity and the Cambrian explosion is not a single line of consequence. It is a network of overlapping processes: tectonic renewal, chemical weathering, sediment burial, ocean oxygenation, and biological innovation all playing out across tens of millions of years. Some scientists argue that the oxygenation pulse predates the explosion. Others suggest it lagged behind. The truth is probably both. The Earth was building potential, storing it in chemistry until the biological system could make use of it. When you stand at the rim of the Grand Canyon today and trace your finger along the Great Unconformity, you're touching this very transition. Below your fingertip lies the silence of vanished time, the crystalline basement stripped to its roots. Above it lie the first whispers of complexity, the sandstones and limestones laid down as life began to flourish. The line between them is not just a gap in rock, it is the seam between 2 modes of existence, one geological, one biological. In a way, the Earth's greatest erasure became its greatest opportunity. The same processes that destroyed the old record, ice, weather, and chemical dissolution, prepared the surface for new stories. Without that destruction, the oceans might never have received their nutrient pulse, and complex life might have remained potential rather than history. The missing billion years were not wasted, they were converted. The memory of the planet was rewritten, not lost. We can see this in the isotopic data from marine carbonates worldwide. After the Neoproterozoic glaciations, the carbon isotope record stabilizes, signaling a shift towards steady-state biogeochemical cycling. Sulfur isotopes show increased fractionation, consistent with the rise of oxygenated conditions. Strontium isotope ratios spike, reflecting intense continental weathering. All these clues point to a planet undergoing systemic change, what geologists sometimes call a geochemical revolution. And so, the Great Unconformity becomes more than a geological oddity. It is a hinge in planetary evolution. Before it, the Earth was a world of microbial mats, iron-rich oceans and barren crust. After it, the seas filled with calcium skeletons, mobile animals, and ecological feedbacks that would shape the next 500 million years. The line in the rock, that silent boundary between granite and sandstone, is also the line between anonymity and autobiography, the moment when life began to inscribe its presence onto the surface of the world. Even now, scientists continue to test this connection. Geochemical models simulate how massive erosion could have altered seawater composition. Experimental petrology investigates how glacial grinding exposed reactive minerals. Oceanographers study how calcium-magnesium ratios affect biomineralization. The consensus is not final, but the pattern is unmistakable. A geological forgetting preceded a biological remembering. It is humbling to think that the world's most creative moment may have required such vast destruction. The billion years that vanished gave rise to the billion years that followed. A new kind of planet, one capable of thought, perception, and memory. What began as a planetary silence ended as a chorus of complexity. Standing today before those cliffs, you can almost sense it. The sound of deep time turning a page. Imagine this. The year is 1788. You're standing on a cold, windswept shore in Scotland, where the cliffs near Sicker Point reveal an unsettling geometry. 2 layers of stone meeting at a perfect impossible angle. Below you lie steeply tilted slabs of ancient grey-wacke, hardened from deep-sea mud long ago. Above them rest younger, horizontal beds of red sandstone laid down in rivers and deserts. Between them runs a thin, undramatic seam, a line of contact so ordinary you could miss it, yet so profound it rewrites everything humans thought they knew about time. James Hutton stares at that boundary and feels vertigo. The world, he realises, is far older than any book has dared to suggest. Hutton called it an unconformity, a break in the record, a gap in time where erosion had destroyed one world before another began. In that single outcrop, the Scottish coast revealed what no clock or scripture ever had. The Earth was not a few thousand years old, but incomprehensibly ancient. The phrase he used still humbles geologists today. We find no vestige of a beginning, no prospect of an end. In those words, deep time was born, not as an abstraction, but as a physical observation in stone. It is hard now to imagine the shock that idea caused. In the late 18th century, the dominant belief was that the planet's surface had been shaped by a few brief catastrophes, floods, earthquakes, divine acts compressed into a short chronology. To claim that countless ages of deposition, uplift and erosion had sculpted these rocks was nearly heresy. But Hutton saw something that could not be unseen. The vertical layers beneath his feet had once been horizontal, laid down as marine sediments, then buried, tilted upright by tectonic forces, and later worn flat by erosion. Only after immense intervals of time were new sediments deposited atop them. To produce such a sequence required not one lifetime of a planet, but many. Hutton's insight, born from the Scottish coast, quietly seeded a revolution. His contemporaries could barely comprehend the scale he implied. When he published his theory of the Earth in 1788, he spoke of the planet as a self-renewing machine, a system of endless cycles. Mountains rose and crumbled, sediments washed into the sea, were compacted into new rock, then uplifted again. The Earth, in Hutton's view, was not decaying from creation, but perpetually recycling itself. It was a world of process, not event. Decades later, that same idea would be rediscovered on the other side of the world. In the late 1800s, geologists exploring the American West began to encounter unconformities on an even grander scale. At the Grand Canyon, John Wesley Powell and his contemporaries mapped a boundary so vast it stretched across continents. Beneath it lay ancient metamorphic and igneous basement rocks, granites and schists billions of years old. Above it, younger Cambrian sandstones lay almost casually, separated from their basement by a surface of erosion representing hundreds of millions of missing years. Powell called it the Great Unconformity. What Hutton saw in miniature at Sicker Point, the Grand Canyon revealed in panorama. To early explorers, the scale was overwhelming. The canyon's vertical walls were like the pages of an open book, except the first 1,000 chapters had been torn out. Victorian geologists, armed with compasses and notebooks, traced those boundaries mile by mile, measuring angles, noting the contrast between crystalline basement and horizontal cover. They began to suspect that this was not an isolated phenomenon but a global pattern, a silent gap uniting distant continents. The phrase lost time took on literal meaning. For those early field scientists, every discovery was both empirical and existential. Imagine carrying a canvas field bag across the baking Colorado Plateau, hammering off fragments of schist so ancient that no life had yet crawled upon the land when it formed. Imagine looking up to see those ancient rocks capped abruptly by younger sandstone full of ripple marks, traces of shallow water and sunlight. Between them, nothing. No fossils, no sediments, just a clean erosional surface that represented perhaps 1 billion years of missing story. It was as if nature itself had censored its own autobiography. The 19th century was the great age of geological literacy. Everywhere, scientists were learning to read the planet. Outcrops became paragraphs. Formations became chapters. Hutton's insight evolved into the principle of uniformitarianism, later refined by Charles Lyell. The idea that the same processes we see today, rain, rivers, volcanoes, earthquakes, have been shaping the Earth for eons. Deep time was no longer philosophical. It was measurable, mappable, and written in the strata. By the mid-1800s, geology had become a public fascination. Illustrated atlases depicted the layers of Britain, France, and North America like rainbow cakes of rock. Museums displayed fossils arranged by age, each labelled with its formation and era. To the Victorian imagination, time became tangible, something one could hold in a fossil or trace on a cliff. Yet beneath all the triumph of classification, the Great Unconformity remained a haunting absence. The more clearly geologists defined the timeline, the more obvious the missing chapter became. The human story of that discovery is as much about patience as intellect. Field geology in that era was grueling. There were no satellites, no radiometric dating, no aerial surveys, only boots, compasses, and sketchbooks. The pioneers of deep time measured with their eyes and their endurance. They waded rivers, climbed cliffs, endured heat and frost, chasing discontinuities through valleys and across deserts. At Sicker Point, Hutton's friend John Playfair wrote of the experience with awe. The mind seemed to grow giddy by looking so far into the abyss of time. That feeling, the dizzy humility before ancient processes, is still what drives geologists today. As the 19th century gave way to the 20th, the language of unconformities matured. Scientists began naming and classifying them: angular unconformities, disconformities, nonconformities, paraconformities. Each represented a different flavour of absence, tilting, erosion, or simply a pause in deposition. The Great Unconformity, however, dwarfed them all. It wasn't a local quirk, but a planetary event. The more global mapping improved, the clearer it became that this gap appeared across nearly every ancient continent. By the time radiometric dating arrived in the early 20th century, the scale of the absence could finally be quantified. Beneath the unconformity, basement rocks yielded ages in the billions of years. Above it, Cambrian sediments dated to roughly 500 million. Between them stretched nearly 1 billion years unrecorded, a gulf vaster than all of human history multiplied 100,000 times. For the first time, the abstract term deep time acquired a number, but even before isotopes confirmed it, field geologists knew intuitively that they were dealing with something colossal. They saw the effects of that gap everywhere: planned surfaces, truncated folds, ancient mountain roots exposed and smoothed before younger sediments buried them anew. The Earth, it seemed, had wiped its own slate clean. The philosophical shock of deep time cannot be overstated. Before Hutton, time was a human scale, centuries, perhaps millennia. After Hutton, it became a cosmic dimension. The human mind, unaccustomed to thinking in billions, struggled to grasp it. Even Charles Darwin admitted that the notion of such vast durations made him uneasy. It was difficult to imagine evolution or erosion proceeding on that canvas. Yet without that scale, nothing in geology or biology makes sense. The Great Unconformity, discovered by patient observation rather than instrumentation, thus became one of the foundations of modern science's worldview. It demonstrated that the Earth was not static but dynamic, not youthful but ancient, and that absence could be as informative as presence. The missing record was not failure, but evidence of change. If you visit Sicker Point today, the rocks still speak softly of that revelation. The lower beds, grey and hard, angle steeply into the North Sea. Above them, the red sandstones lie flat and serene. Between them runs the line that birthed geology as a historical science. Tourists might step over it without noticing, but for those who know what it means that contact is sacred ground, a hinge between worlds. At the Grand Canyon, you can trace the same lesson on a grander scale. Stand on the south rim as the light of evening sweeps across the cliffs, and you'll see it, the ancient Vishnu schist below, the younger Tapiats sandstone above. The gap between them represents nearly a quarter of Earth's history, yet no monument marks it. Only the rocks themselves, their silence eloquent enough. It took centuries for humanity to learn to hear that silence. Each generation of geologists refined the story, mapping, measuring, comparing notes from opposite sides of the globe. What began as a philosophical observation in Scotland became a planetary pattern, recognised from Wyoming to Western Australia. The line between old and new, between basement and cover, became a symbol of continuity through destruction. By the early 21st century, the Great Unconformity had become both a scientific puzzle and a cultural metaphor. Artists, philosophers and poets borrowed the phrase to describe absence, loss and renewal. But it began, as all great scientific ideas do, with people willing to look closely at the ground and ask what the evidence truly meant. When James Hutton looked at that Scottish cliff, he could not have imagined satellites mapping plate motions or mass spectrometers measuring isotope ratios. Yet the question he asked still defines geology today. How do we read the planet's memory when so much of it has been erased? The Great Unconformity remains the physical answer to that question, a reminder that knowledge often begins not with discovery, but with noticing what is missing. Imagine this. You could travel from the base of the Grand Canyon to the red cliffs of Namibia, from the worn heart of Australia to the icy coast of Scandinavia, and beneath your feet you'd still find the same silence, a single line of missing time hidden under different skies, connecting continents that have drifted oceans apart. The Great Unconformity is not local, it is planetary. Wherever we look deep enough, the story repeats itself. Old crystalline basement rocks stripped bare, then overlain by younger Cambrian sediments that seem almost too eager to begin again. Modern geology calls this pattern the global expression of the Great Unconformity, and its reach is astonishing. In North America, it is carved into the backbone of the continent, from Arizona's Grand Canyon to the Black Hills of South Dakota, from the Ozark Plateau to the Adirondacks. In each place the details differ, but the message is the same. A missing billion years between the basement and the sea. In the canyon, it's the Vishnu schist and the Tapeat sandstone. In the Midwest, it's ancient granite overlain by shallow marine dolostone. The contact surface, sometimes razor-thin, sometimes meters thick with weathered clay, speaks of immense erosion before the first Cambrian seas advanced. Move across the Atlantic to Scotland, Norway, and the Baltic Shield, and the pattern reappears. In Norway's Hardangervidda Plateau, Archean and Proterozoic gneisses lie truncated beneath thin layers of Cambrian sandstone and shale. The rocks of Finland and Sweden show the same story. Polished crystalline bedrock, overlain by transgressive marine deposits, with isotopic evidence of weathering that predates the Cambrian. These aren't coincidences of local geology. They are echoes of the same ancient episode of planetary renewal. In Africa, too, the story is unmistakable. Along the margins of the Congo and Kalahari cratons, deeply weathered basement surfaces, etched and planed by long-vanished erosional processes, are overlain by late Neoproterozoic and Cambrian sediments. In Namibia, where the Damara Belt once joined with the crust of South America, you can walk from Precambrian basement through folded Neoproterozoic strata, and find, at the top, the same erosional surface that appears half a world away in Arizona. It's as though the planet pressed reset across every continent at once. Australia preserves one of the most striking versions of this record. In the Northern Territory, the ancient basement of the North Australian Craton is capped by sandstones of the Centralian Superbasin. These early Cambrian sediments rest directly upon surfaces that had been exposed and chemically weathered for eons. Thermochronological studies, using the slow decay of isotopes like helium in apatite and fission tracks in zircon, show that vast areas of crust cooled through the same thermal window between roughly 800 and 500 million years ago. That synchronized cooling suggests not a local uplift, but a global process of exhumation and erosion. The crust everywhere was brought to the surface, scraped clean, and then reburied. South America tells a similar tale. In Brazil, beneath the Parnaíba Basin, ancient crystalline rocks sit directly under early Paleozoic sediments. Along the Andes, older metamorphic belts are truncated beneath flat-lying Cambrian to Ordovician strata. The pattern extends across the ancient core of the continent, hinting that the forces that stripped North America also touched Gondwana's bones. The Andes we see today are much younger, but beneath them lies the ghost of that same lost surface. What ties all these places together is not a single catastrophic event, but a coordinated sequence of planetary processes. Through the lens of plate tectonics and thermochronology, scientists see a world transitioning from one supercontinent to the next. When Rodinia broke apart around 800 million years ago, it exposed enormous continental interiors to erosion. Later, when fragments drifted together again to form Gondwana and Laurentia's proto-North America, new mountains rose and weathered, repeating the cycle. The result was a global period of crustal thinning, uplift, and resurfacing that, combined with glaciation, produced the Great Unconformity surface we now recognise across continents. Modern thermochronology provides a kind of thermal autobiography for the crust. By measuring the retention of isotopes in minerals that cool as rocks move toward the surface, scientists can reconstruct burial and erosion histories. These data show synchronous patterns across distant regions. In North America, zircon and apatite records indicate rapid exhumation and cooling between roughly 700 and 500 million years ago. In Africa, the same time frame marks cooling through similar temperature ranges, consistent with erosion on a continental scale. Even Antarctica, where bedrock exposures are scarce, reveals analogous patterns beneath its ice, the hidden continuation of the same lost world. The tools used to detect these echoes are as intricate as they are poetic. Thermochronologists measure when minerals cooled below specific closure temperatures, like geologic thermometers frozen in time. When these closure ages align across continents, they reveal shared tectonic histories. Mapping such data, researchers visualize ribbons of crust that cooled and stabilized together. Continental fragments once connected, later separated by oceans, but still carrying the same scars. It's as if the Earth's crust retains a synchronized heartbeat that pulses through the ages. Satellite gravimetry, seismic tomography, and global crustal models add further depth to this picture. The ancient cores of continents, cratons, show signs of uniform thinning near their margins, exactly where the Great Unconformity is most pronounced. This thinning corresponds to large-scale lithospheric erosion during the late Neoproterozoic, when continents experienced both rifting and glacial loading. It was not just the surface that was stripped, parts of the underlying crust were thermally rejuvenated. Beneath the geological calm of today's continents lie the deep scars of that restructuring. Even the chemistry of weathering profiles supports this global connection. Across continents, the surfaces immediately beneath the unconformity display signatures of ancient tropical weathering, kaolinite clays, iron oxides, and isotopic ratios consistent with prolonged exposure to rain and air. That means before the Cambrian seas advanced, the continents were not buried under glaciers or oceans. They were landscapes, open to the sky, undergoing slow chemical erosion. The world had spent millions of years sculpting itself down to its roots, one atom at a time. When those landscapes finally drowned beneath transgressive seas, they became time capsules. The first sediments laid atop them record the chemistry of that transition. Sandstones rich in quartz from continental abrasion, shales with the isotopic evidence of changing ocean chemistry, carbonates signalling new biological productivity. Together they form a planetary horizon, a synchronized restart of sedimentation after 1 billion years of loss. What makes this so remarkable is not just the repetition, but the precision of that repetition. The same surface within the same window of time appears across continents that had already drifted far apart. That tells us that the processes shaping the Great Unconformity were not regional quirks. They were global forces operating through the connected system of Earth's crust, oceans, and atmosphere. It's humbling to think that the same surface you can touch at the rim of the Grand Canyon once stretched, in a geological sense, beneath deserts, jungles, and polar ice caps. The crust we stand on has been recycled so many times that what seems solid beneath our feet is really just a temporary arrangement of atoms in motion. The Great Unconformity is the memory of that rearrangement, an alignment of absences linking all continents like seams in an ancient book. In recent decades, high-resolution thermochronology has revealed still more subtle patterns. In some regions, like the Canadian Shield, the basement cooled twice, once during Rodinia's breakup and again during the Cambrian burial. In others, such as Western Australia, the cooling coincides exactly with the timing of global glaciations. These variations show that while the planet experienced a shared transformation, each continent recorded it in its own dialect of temperature and time. The Great Unconformity is not one line, but a chorus of local silences harmonized into a global refrain. The implications are profound. When scientists overlay these patterns on reconstructions of ancient supercontinents, the boundaries match remarkably well. It suggests that the processes that erased the record were linked to the same tectonic reconfigurations that prepared the planet for new biological complexity. Erosion, uplift, and sedimentation were not isolated events. They were global systems interacting over hundreds of millions of years. Even now, the Great Unconformity continues to teach us humility. The more precisely we map it, the more we realize how interconnected the planet truly is. The same missing chapter lies beneath our cities, our mountains, our oceans, sometimes buried deep, sometimes exposed to the sun. The continents carry it like a shared scar, a reminder that memory and loss are not opposites in geology but partners in the same story. So next time you stand on ancient rock, whether it's a granite outcrop in Canada, a sandstone cliff in Namibia, or a polished gneiss in Norway, remember that you are standing on the same line of absence. 1 billion years vanished here, the same billion that vanished there. The Earth forgets in unison, and through that forgetting it remembers what it means to begin again. Imagine this. You're standing at the edge of Greenland, where the ice meets the sea in a slow, endless collapse. Beneath the white silence, thousands of meters of frozen weight press down on the crust, grinding, polishing, and carrying away everything in their path. At the glacier's base, crushed rock becomes flour. Rivers of sediment-laden meltwater roar through subglacial tunnels, and particles of ancient granite are swept toward the ocean. This is what forgetting looks like in real time. A planet erasing its own surface with patience measured not in centuries but in kilometers of ice. To understand the Great Unconformity, the billion-year gap carved into Earth's memory, we turn to the living laboratories of ice that remain. Greenland, Antarctica, and the ancient shields of North America and Scandinavia. These places let us watch, in miniature and in motion, the same processes that once scoured the continents to their crystalline foundations hundreds of millions of years ago. They are not metaphors for the past. They are its echoes, repeating under colder skies. Under the Greenland ice sheet, the pressure of ice is immense, up to 100 atmospheres at depth. That weight does more than compact snow into ice. It transforms the crust beneath it. Friction and geothermal heat melt the ice base slightly, creating a film of water that acts as both lubricant and solvent. The glacier no longer simply slides over the bedrock. It grinds it down, plucking and pulverizing it into fine sediment known as glacial flour. Every year, Greenland's meltwater carries nearly 1 billion tons of this powdered rock into the ocean, tinting fjords turquoise with suspended minerals. Multiply that process by millions of years, across every continent, and you begin to glimpse how an entire geological record could vanish. Antarctica offers another version of this story, slower, deeper, more absolute. Beneath its 2 great ice sheets lies a buried world of mountains and valleys, invisible to the eye but mapped by radar and gravity. These landscapes, hidden for millions of years, are still being reshaped by ice. Some of the bedrock beneath East Antarctica has been polished to mirror smoothness, stripped of weathered soils and sediments. In West Antarctica, fast-moving ice streams gouge troughs kilometers deep, carrying debris far into the Southern Ocean. When that ice retreats, it leaves behind a surface as mute and clean as the ones preserved beneath the Great Unconformity, bare rock scoured of history. The mechanics of glacial erosion are both brutal and elegant. At the base of the ice, fragments of rock freeze into the glacier, turning it into a moving file of sandpaper. As the glacier advances, these embedded stones scratch and grind the bedrock, carving striations that all point downslope, a record of direction frozen in stone. In places like the Canadian Shield, you can still walk across polished granite surfaces grooved by the last ice age, their glacial scratches aligned like compass needles. These are the same kinds of marks we find on Precambrian surfaces beneath the Great Unconformity, faint signatures of ancient ice long vanished. Yet glaciers don't just remove, they also rearrange. They transport eroded material over vast distances, sorting it into moraines, outwash plains and submarine fans. In modern fjords, sonar surveys reveal sediment plumes spreading far offshore where fine particles settle into quiet basins. Some of the world's most productive continental shelves, off Greenland, Alaska and Norway, are built from these deposits. The same must have happened in the Neoproterozoic. The continents stripped bare while the oceans accumulated their lost material, burying it under kilometres of sediment that would later harden into new rock. Erosion and creation were two sides of the same glacial breath. In Canada's Arctic, geologists studying modern ice streams use satellite imagery to measure glacial movement by the metre. They see how ice accelerates when it encounters lubricating water at its base, how melt pulses surge in summer, and how pressure waves within the ice can change flow rates across entire valleys. These observations help model ancient conditions when ice sheets perhaps thousands of kilometres across could have scoured whole continents during the late Precambrian. The scale differs, but the physics remain the same. Ice erodes through time, heat and movement. One of the most powerful lessons modern glaciers teach us is the permanence of impermanence. In places like Iceland or Alaska, retreating glaciers expose freshly stripped rock surfaces, raw, lifeless, shining with moisture. Within years, lichens and mosses begin to colonize them. Within centuries, soil starts to form. Within millennia, the scars vanish beneath vegetation and sediment. But beneath that new surface lies an indelible boundary, a miniature unconformity marking the moment of erasure. If we could rewind time, every ancient continent would once have looked like this, a network of glacial wounds slowly healing, the crust beginning again from zero. The evidence for this kind of global-scale glacial erosion survives in the world's oldest landscapes. The Canadian Shield, the heart of North America's crust, is a natural museum of these processes. Its rocks have been repeatedly planed by ice sheets over billions of years. The exposed granites and gneisses, some nearly 4 billion years old, are cut by smooth surfaces and striations that mirror those of Greenland today. Even the pattern of drainage, thin soils, countless lakes and aligned valleys, speaks of glacial excavation. The shield shows how ice transforms not only rock, but geography itself, dictating where water flows and where new sediments will form. Similar evidence appears in Scandinavia, where ancient Precambrian bedrock has been reworked by dozens of quaternary glaciations. In Norway, polished gneisses gleam under thin layers of soil, while fjords trace the paths of former ice tongues. In Finland and Sweden, flattened uplands and erratic boulders record the slow retreat of ice that sculpted the landscape we see today. These features are not just remnants of the last ice age. They are living analogues for what the Earth endured before the Cambrian, when glaciers were far more extensive, lasting millions rather than thousands of years. The chemical consequences of glaciation are equally revealing. When ice grinds rock to powder, it increases the surface area exposed to chemical weathering. As the meltwater flows to the ocean, it carries dissolved ions that alter seawater chemistry. Modern measurements show that glacial runoff is rich in calcium, silica and iron, the same ingredients that changed Earth's oceans in the wake of the Great Unconformity. The link between mechanical erosion and chemical transformation is direct. Glaciers scrape away, rivers dissolve, and oceans evolve. It is the same cycle repeating under modern conditions, only smaller and faster. Scientists studying Antarctic melt streams have even tracked the journey of isotopes from crushed bedrock into the Southern Ocean. These isotopic fingerprints reveal how glacial erosion contributes to nutrient fluxes that sustain plankton blooms, tiny, modern echoes of the chemical fertilization that may have triggered life's Cambrian expansion. When we watch the waters flowing from under Antarctic ice today, we are looking at the continuation of a process that began hundreds of millions of years ago, years before there were animals to record it. One of the most compelling modern parallels lies in the Greenland fjords, where glaciers retreat dramatically each summer. As they do, they release plumes of fine sediment that spread across the ocean's surface, visible from space as turquoise clouds. Beneath those plumes, oceanographers find dense layers of suspended sediment, descending like slow rain to the seabed, forming annual deposits measurable in millimetres. Over geological time, such accumulation can build hundreds of metres of stratified mud and sand. It is easy to imagine that the lost billion years of continental rock now rests in similar ancient basins, buried deep under later sediments, transformed by pressure into slate and quartzite. And yet, for all we learn from modern glaciers, they remain incomplete analogues. The ice sheets of today, immense though they seem, are shadows of their predecessors. The pressures and durations of ancient glaciations dwarf anything we can observe directly. But by studying these smaller systems, we glimpse the mechanics of a world-scale transformation, how abrasion, plucking and subglacial melt can reshape a continent's surface into a single, planar unconformity. The same physical processes, extended over tens of millions of years, could plausibly strip away a billion years of crustal record. There is a quiet irony in this realization. To understand one of the oldest mysteries in geology, we must look to the youngest landscapes on Earth, the retreating edges of modern ice. They show us not just how the planet forgets, but how it prepares to remember again. Because glaciers are not simply agents of destruction, they are also curators. They erase one history to make room for another, transporting the old into new forms, burying the debris of continents where it can one day re-emerge as mountain or seafloor. The story of the Great Unconformity is still unfolding under our eyes, written in meltwater, sediment, and light. Perhaps that is the most humbling insight of all. The ice beneath our current climate may be temporary, but the forces it represents are eternal. Erosion and renewal, loss and record. These are not past events, but ongoing habits of a restless planet. Every polished granite boulder, every turquoise plume off Greenland, is a whisper from the deep past reminding us that time, like ice, moves in cycles of forgetting and return. Imagine this: the Himalayas, the Alps and the Rockies, all gone. Not tomorrow, not next millennium, but someday, ground into silt, recycled into rivers, their peaks worn to plains and their memory sealed beneath new sediments. Every mountain you've ever seen or climbed already has an expiration date. The only question is how long it can defy gravity before it becomes sand again. Geologists have a quiet joke about this. The warranty on most mountain ranges expires after about 50 million years. It's not a precise number, of course, but it captures a truth that no peak, however majestic, escapes the slow patience of erosion. Mountains, for all their defiance, are temporary gestures of the crust. They rise from collisions between tectonic plates, their birth marked by earthquakes, volcanism, and thrust faults, but the same forces that build them also sow their destruction. From the moment a mountain begins to rise, it begins to fall. Wind, rain, glaciers and gravity wage an unending campaign against elevation. Tiny cracks deepen with freeze and thaw. Rivers carve valleys that widen imperceptibly year after year. Entire slopes crumble in landslides, returning the rock to sediment, ready to begin the cycle anew. The planet's highest monuments are, at heart, ongoing negotiations between uplift and decay. The process is slow, but relentless. The Himalayas, the youngest and tallest range on Earth, are eroding at an average of 1 millimetre per year. That might not sound like much, but over 10 million years, it's 10 kilometres, enough to remove the full height of Everest. The only reason the Himalayas still exist is that India continues to push into Asia, forcing the crust upward as fast as erosion wears it down. If that motion ever stopped, the peaks would quietly melt back into the plains within a few tens of millions of years. In the Appalachians, that process is already nearly complete. Once as tall as the Himalayas, they've been worn to rounded hills by hundreds of millions of years of weather. The ancient crystalline cores that remain are less mountains than memorials to mountains. Erosion is not uniform either. Climate, vegetation and rock type all play their part. In humid regions, chemical weathering dominates. Rainwater mixes with carbon dioxide to form weak acid that dissolves minerals and carries them to the sea. In arid regions, physical breakdown rules. thermal expansion, frost cracking, and the steady grinding of windblown sand. Glaciers carve the most aggressively of all, plucking entire valley walls as they advance. If you stand in a U-shaped alpine valley, you're standing in a sculpture carved by ice. The slow melt of those glaciers leaves behind talus slopes, moraines, and braided streams, all reminders that every mountain eventually collapses under its own magnificence. But the story of decay is not one of loss alone. Erosion feeds creation. As mountains shed their mass, they unburden the crust beneath them. The weight of rock removed by rivers and glaciers allows the underlying lithosphere to rebound upward in a process called isostasy. It's geological karma. Remove the load, and the surface lifts to compensate. That's why even ancient eroded shields like Canada's or Scandinavia's are still rising today, by a few millimetres per year, as they recover from both erosion and the melting of Ice Age glaciers. In deep time, the crust behaves less like stone and more like a slow fluid, always seeking balance. This feedback between erosion and rebound creates a self-regulating system. When uplift increases, so does erosion, because higher slopes mean faster rivers and stronger weathering. When erosion lowers relief, uplift slows. Over millions of years, the two processes reach a kind of uneasy equilibrium, a dynamic tension that shapes the face of continents. Some scientists call this topographic steady state, though nothing in nature is ever truly steady. The Earth is constantly adjusting, breathing in geological time. What we see as majestic mountain ranges are snapshots in an unending cycle. If we could accelerate time, we'd see them rise and fall like waves, continents colliding and parting, surfaces erased and rewritten. The Appalachians gave way to the Rockies. The Rockies will one day give way to whatever range forms when the Pacific Plate dives deeper beneath North America. The crust forgets its shapes, but never its motion. The materials of those vanished mountains don't disappear either. They simply change form. The grains of sand on a beach may once have been granite from a vanished peak. The clay in a floodplain may have formed from feldspar that weathered out of an ancient batholith. Even the limestone beneath your feet might owe its calcium to rocks once lifted high above sea level. Mountains die into the sea, and from the sea they rise again. The Great Unconformity was not an exception to this cycle. It was a particularly thorough act of planetary renewal, one phase in the continuous rhythm of construction and erasure. To grasp the scale of these processes, consider the lifespan of an entire tectonic cycle, from supercontinent to supercontinent. Every 400 to 600 million years, continents collide, merge, and break apart again. Each collision builds new mountain belts, each breakup erases them. The erosion of one supercontinent seeds the sediments of the next. The crust doesn't age uniformly, it pulses. The Himalayas are the latest expression of this ongoing heartbeat, destined to crumble into the Indian Ocean just as their predecessors did. Even today, we can watch the early stages of this forgetting. Satellite data show Himalayan rivers carrying billions of tons of sediment toward the Bay of Bengal every year. The Mississippi transports nearly 200 million tons of silt from the Rockies and Appalachians to the Gulf of Mexico annually. Across the Andes, wind-blown dust fertilizes the Atlantic with nutrients eroded from high plateaus. Erosion is not destruction, it's distribution. The mountains are not lost, they're just spread thinner. One could say that the Great Unconformity was simply the planet's most ambitious cleanup job. But that same principle applies now, in miniature, across every range. The Alps are losing centimetres each century to freeze-thaw weathering. The Pyrenees, no longer tectonically active, are deflating faster than they're being lifted. Even Antarctica's transantarctic mountains, among the oldest continuous ranges on Earth, are quietly subsiding under their own ice, waiting for another glacial cycle to bury or expose them anew. In deep time, silence comes for every summit. There's a certain comfort in this perspective. Mountains seem eternal only because we measure them in human time. To the planet, they are as fleeting as waves. What we call stability is simply slowness. Our civilizations cling to the brief calm between upheavals, mistaking it for permanence. But if the Great Unconformity teaches anything, it's that nothing in the crust stays remembered forever. The rocks beneath our cities will one day be stripped, planed, and recycled into another future surface. perhaps beneath a sky entirely different from ours. Geologists like to quantify such things, even if the numbers are absurdly large. Average continental erosion rates hover around 10 to 100 meters per million years, depending on climate and relief. At that pace, it takes 10 million years to remove a single kilometer of rock. It sounds glacial, until you recall that Earth has had more than 4 billion years to work with. At that scale, every mountain range that has ever existed has also vanished. The cycle is not only inevitable, it is complete. There's even a touch of humour in how the planet handles these matters. We spend lifetimes protecting landscapes that the Earth itself regards as temporary drafts. The Grand Canyon, breathtaking as it is just a brief incision between uplift and collapse. The Himalayas, icons of immensity, are but wrinkles on a restless crust that keeps ironing itself flat. The Earth doesn't destroy beauty, it just prefers impermanence. When we look forward tens of millions of years, we can already predict the next acts of this ongoing play. Africa is drifting northward, set to collide with Europe. The Mediterranean will close, giving birth to a new mountain range that may one day rival the Himalayas. Meanwhile, the Atlantic is slowly widening, its mid-ocean ridge extruding basalt that will become tomorrow's continents. The cycle continues, patient as gravity, deaf to human timelines. And someday, far beyond our imagination, today's mountains will form the basement of another Great Unconformity. The remnants of the Rockies, the Andes and the Alps will lie exposed and eroded, their sediments compacted into new strata. Future geologists, perhaps not human ones, will look at that boundary and puzzle over the missing eons. They'll wonder what erased the record. The answer will be the same as it ever was: time and the quiet efficiency of erosion. It's a strange comfort to think that even silence leaves patterns. The Great Unconformity is not a pause in the Earth's story, it's punctuation. Every comma and period in the geological record is carved by erosion, by forgetting. If our mountains are falling silent, they are only returning to the rhythm that made them. So if you ever find yourself in the mountains, remember, you're standing in mid-sentence. The story is still being written, still being erased, still being told. The peaks are temporary, the plains inevitable, and the cycle endless. The Earth will continue to sculpt and forget, long after we've stopped listening. Imagine this. Two geologists staring at the same cliff face, both tracing the same sharp boundary with their fingers, and yet each seeing a different planet beneath it. One sees the handiwork of ancient glaciers, vast and global, planing continents clean under kilometres of ice. The other sees tectonic forces and uplift, continents colliding, crust rising, mountains eroding, and basins sinking. Both are looking at the same line, the Great Unconformity, but their stories of how it formed diverge sharply. This is not a conflict of belief, but of data. 21st century geology finds itself at one of those rare crossroads where new tools have outpaced old assumptions, and the rocks are making scientists argue in the most productive way possible. The central question is deceptively simple. What carved away nearly 1 billion years of Earth's record from every continent? The simplest answer, ice, was once considered elegant enough to explain it all. The theory proposed that during the Snowball Earth episodes roughly 700 million years ago, glaciers ground away enormous volumes of crust, stripping the continents bare before the Cambrian seas advanced. The physical plausibility of this is supported by what we see today under modern ice sheets. But thermochronology, our ability to measure when rocks cooled as they approached the surface, has added new complications. It turns out that erosion can leave a thermal signature, and those signatures are not always consistent with a single, global glacial sweep. The glacial model rests on compelling evidence. Around the world, surfaces just beneath the Great Unconformity often show polished striated textures consistent with ice abrasion. Sedimentary basins above the Unconformity contain coarse debris that could have been derived from glacial meltwater. Chemical data, including isotopic shifts in strontium and carbon, around the same period, indicate massive continental weathering consistent with widespread glaciation. Some models even suggest that the weight of these Neoproterozoic ice sheets caused crustal flexing, depressing basins, and enhancing erosion at their margins. The story is straightforward and satisfying. An icy planet, a global reset. But in science, satisfaction is rarely the final word. By the early 2000s, new thermochronological data began to suggest a more complex timeline. Researchers using apatite and zircon, UTH, 𝐓𝐻 dating, methods that measure when minerals cooled below specific closure temperatures, found that in many regions, basement rocks beneath the Great Unconformity cooled and stabilized long before the proposed snowball glaciations. That means they had already been exhumed to shallow depths well before the planet froze. In other regions, cooling occurred later, implying local erosion continued into or after the glacial events. The thermal history of the crust simply didn't line up with a single, global moment of removal. In studies from the Rocky Mountains, the Canadian Shield, and the Grand Canyon, apatite fission track data, tiny radiation scars in mineral grains, revealed that different blocks of crust had very different cooling paths. Some cooled steadily over hundreds of millions of years, suggesting gradual erosion and uplift. Others showed sudden thermal drops, evidence for rapid exhumation, possibly triggered by tectonic events. The global synchronicity implied by the glacial model began to unravel. What emerged instead was a mosaic, a planet where different mechanisms acted at different times, converging on the same visual result: missing rock. This realization brought tectonics back into the picture. During the breakup of the supercontinent Rodinia, beginning around 800 million years ago, continental crust stretched and thinned. Rifting created mountain ranges and basins, exposing deep crustal rocks to the surface in some places while burying them in others. Later, as continents reorganized to form Gondwana, those same regions experienced renewed uplift and erosion. In many cases, the unconformity may record the cumulative effect of this tectonic breathing, rising, eroding, and subsiding over tens of millions of years, rather than a single catastrophic scraping. Thermochronology supports this variability. In the Ozark Plateau and the Appalachian Basement, data show prolonged heating and cooling cycles that align better with rifting and isostatic uplift than with a short glacial pulse. Similarly, studies in Australia and South Africa reveal erosion patterns spanning hundreds of millions of years, too slow and too staggered to match a global ice-driven event. The glacial model may still explain parts of the picture, but it no longer explains all of it. Then there is the third contender: chemical weathering. Long before glaciers or tectonic uplift could expose the basement, the continents may have been sculpted by deep tropical weathering under ancient atmospheres. When carbon dioxide levels were high, rainfall and groundwater would have reacted with silicate rocks to form thick clay-rich regoliths. Over millions of years, these weathered zones could reach depths of hundreds of meters, softening the crust and making it easier for later ice or erosion to remove the weakened material. Evidence for this comes from paleosols, ancient soils, preserved just below some unconformities, as well as isotopic anomalies in elements like aluminum and lithium that signal prolonged chemical alteration. In this model, the Great Unconformity wasn't carved suddenly. It dissolved slowly, like sugar in rainwater. Today, geologists tend to treat these mechanisms not as competitors, but as collaborators in time. In most regions, the unconformity likely represents a sequence. Prolonged weathering weakened the crust, tectonic uplift exposed it, and glaciation finally swept it clean. Yet the balance among these forces varies from continent to continent. In North America, thermochronology suggests strong tectonic and erosional contributions. In Africa and Australia, the surfaces appear more consistent with weathering and later glacial polishing. The phrase "the Great Unconformity" may therefore be misleading. It could be many unconformities, formed by overlapping processes that happen to converge in time. Still, the debates persist because the data themselves are subtle. Thermochronological models rely on assumptions about heat flow and diffusion rates, which can vary with mineral composition and fluid presence. Glacial evidence, while compelling, is often ambiguous when viewed at billion-year timescales. Striations and polish can be mimicked by tectonic shearing or subaerial erosion. And weathering profiles are easily destroyed by subsequent metamorphism. The result is a field where every new paper adds clarity in one corner while deepening uncertainty in another. In recent years, researchers have begun combining these approaches into integrated models, By merging apatite U/He data with cosmogenic nuclear exposure dating and numerical landscape simulations, they can now reconstruct not just when erosion happened, but how fast and under what climatic conditions. For instance, a 2015 study in Colorado combined fission track and zircon helium data to show that the local unconformity likely formed through a combination of tectonic uplift and surface stripping long before global glaciation, but was later modified by it. The result? Both camps were partly right. Advances in thermochronometric software have also transformed the field. Tools like 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 allow scientists to invert large datasets into probabilistic thermal histories, visualizing millions of possible cooling paths for a single rock sample. These models show that even within a single region, the thermal story can vary drastically over short distances. The Great Unconformity, once treated as a simple line, is now seen as a three-dimensional volume of missing time whose boundaries fluctuate through space and history. Meanwhile, field geologists continue to add crucial context. In the Himalayas, comparisons between modern erosion rates and thermochronological cooling suggest that even massive uplift can erase thick crustal sections in surprisingly short periods. Tens of millions of years, not hundreds. That realization reinforces the plausibility of both tectonic and glacial removal acting together at global scale. In Antarctica, subglacial mapping shows that current ice sheets can excavate basins kilometers deep, enough to strip ancient crust clean if maintained over sufficient duration. The physics of such removal no longer seem speculative. If there's a consensus forming, it's a cautious one. The Great Unconformity was not one event, but the confluence of many: tectonic stretching, chemical decay, and episodic glacial scouring woven together across hundreds of millions of years. Each region preserves a slightly different version of the same erasure, stitched into the crust like a patchwork of vanished landscapes. In this way, the scientific conversation mirrors the process itself: gradual, layered, occasionally abrupt. Researchers refine their models, compare data, argue, and revise, eroding old theories, exposing new ones, leaving behind cleaner surfaces of understanding. In the end, the most honest conclusion may be that we will never pinpoint a single cause, only the interplay of causes that shaped a restless planet. And perhaps that's appropriate. The Great Unconformity represents not a singular moment of violence, but a system behaving as systems do, balancing, forgetting, and beginning again. Science, like the crust it studies, advances through cycles of erosion and uplift, its landscape reshaped by each new line of evidence. The gaps in our knowledge are not flaws, they are the space where discovery happens. Imagine this: a planet tidying up after itself. Continents rise, mountains crumble, carbon locks away in stone, and oceans sigh in balance. The surface looks scarred, chaotic, accidental. But underneath, the chemistry hums in loops, feedback so subtle that the entire biosphere and atmosphere depend on them. The Great Unconformity, that billion-year hole in the rock record, might not just be a geological accident. Some scientists have begun to wonder if it was part of the Earth's self-correcting machinery, a planetary reset not to erase history, but to keep the planet habitable long enough for the next chapter to begin. To understand this idea, we have to think in systems, not snapshots. The Earth isn't a passive stage on which life acts. It's an active participant, a layered feedback engine. When mountains form, they don't just decorate the landscape, they draw carbon dioxide from the air through weathering. Rain reacts with silicate minerals, pulling greenhouse gases into rivers, then into the ocean, where they eventually become limestone and marble. That process cools the climate. When erosion lowers mountains, volcanic activity restores carbon dioxide to the atmosphere, warming it again. The system loops endlessly, a thermostat made of stone, water, and air. The late Precambrian world that birthed the Great Unconformity sat at the edge of this balance. Continents were freshly exposed after the breakup of Rodinia, and massive erosion began feeding oceans with ions like calcium, magnesium, and silica. Those reactions pulled down enormous amounts of carbon dioxide, cooling the climate until the planet tipped into glaciation. The glaciers then stripped the crust bare, exposing more reactive rock, which drew down even more carbon. It's the ultimate positive feedback, the kind that gets out of control fast. At some point, perhaps the only way for the planet to regain stability was to remove the overreactive material entirely, to plane itself smooth and let volcanism rebuild the chemical balance from scratch. A cosmic version of clearing cache files. Modern Earth system models show just how powerful that rock weathering feedback can be. A change in mountain area or uplift rate of only a few percent can shift global temperatures by tens of degrees over geologic timescales. In simulations, the rate of silicate weathering acts as a governor on atmospheric composition. When volcanoes emit more carbon dioxide, the planet warms, precipitation increases and weathering accelerates, pulling carbon back down and cooling the planet again. When volcanism wanes, weathering slows, allowing the atmosphere to rebuild greenhouse gases. No conscious control, no design, just physics finding equilibrium through cycles of erosion and burial. During the billion years that disappeared beneath the Great Unconformity, this thermostat may have gone into overdrive. Tectonic uplift created fresh rock surfaces. Glacial cycles pulverized them. Chemical reactions drained carbon dioxide to levels low enough to trigger snowball conditions. Once the ice retreated, the excess sediments buried much of the carbon they had locked away, rebalancing the atmosphere. The whole sequence, tectonics, weathering, glaciation, burial, reads like the planet's immune system restoring equilibrium after a fever. The missing rock isn't a wound, it's a scar from healing. The geochemical evidence fits the pattern. Carbon isotope records from marine sediments before and after the gap show enormous swings, the kind only explainable by planet-scale perturbations to carbon cycling. Strontium isotopes indicate that weathering rates spiked during these intervals, consistent with freshly exposed crust being chemically digested by rain and ocean water. Even the distribution of rare earth elements in post-gap sediments implies an ocean flooded with ions freshly liberated from continental rock. The system wasn't broken, it was rebalancing through erasure. From a modelling perspective, this self-regulation is astonishing. Climate modelers use coupled carbon-silicate cycle simulations to estimate how fast feedbacks operate. In these models, the drawdown of carbon dioxide through weathering is sensitive to both temperature and exposed land area. When the planet warms, weathering accelerates, cooling it again, a negative feedback. But if erosion or tectonic processes drastically increase land exposure, as happened when Rodinia broke apart, the negative feedback can overshoot, removing too much greenhouse gas and plunging the climate into global freeze. Once that happens, ice itself shuts down weathering by sealing the continents, giving volcanism time to rebuild carbon dioxide. When the ice finally melts, the climate stabilizes at a new equilibrium. The rock record lost 1 billion years, but the system gained resilience. The analogy isn't mystical, it's mechanistic. Every weathered mineral, every dissolved ion, every buried carbonate is part of an equation that the planet constantly solves for stability. The Great Unconformity may be the signature of that equation being recalculated on a grand scale. The planet raised part of its surface to rewrite the conditions for life. This feedback interpretation also helps explain why the unconformity appears worldwide, yet formed asynchronously. Local erosion events, driven by tectonics or glaciation, could all feed into the same global chemical cycle. No single catastrophe was needed, just many small contributions to a planetary bookkeeping process. Each continent's erosion changed atmospheric chemistry, which altered climate, which in turn influenced erosion somewhere else. The line we call the Great Unconformity might simply be the place where those loops converged, the stratigraphic record of the planet balancing its own equations. Even today, Earth still runs on the same feedback principles. The Himalayas are currently drawing down carbon dioxide through intense monsoon weathering, a process measurable in the chemical composition of rivers like the Ganges and Brahmaputra. Over millions of years, that reaction will cool the global climate, perhaps even nudging it toward another ice age. In Greenland, meltwater carries ground-up minerals into the ocean, fertilizing phytoplankton that capture carbon and sink it to the deep sea. Every storm, every landslide, every drop of rain contributes a small line of code to the planet's ongoing computation of balance. The idea of planetary feedback loops isn't new, but the data supporting them have become much richer in the past 2 decades. Satellite observations track chemical weathering from space. Geochemical proxies in deep-sea sediments show how atmospheric carbon dioxide fluctuated across glacial and interglacial cycles. Even laboratory experiments have replicated silicate weathering reactions under controlled conditions, confirming their temperature sensitivity. Together, these lines of evidence suggest that Earth's stability is not a miracle. It's the emergent property of rock, water and time cooperating through physics and chemistry. Of course, feedbacks can fail. When the system's pace of disturbance outstrips its pace of correction, climate tips into new states, as it did in the Permian extinction or during rapid ice melt events. The Great Unconformity might represent one such pivot point, a boundary between old feedback regimes and new ones. In that sense, the planet didn't just remove a billion years of rock, it retired an old feedback circuit and replaced it with one capable of sustaining more complex life. The surface was reset, the climate recalibrated, and the oxygenation and nutrient conditions for the Cambrian explosion were, perhaps unintentionally, prepared. There's a quiet elegance to that view. The Great Unconformity ceases to be a gap and becomes a hinge, the pivot between an unstable early Earth and a self-regulating modern one. It's the geological equivalent of an organism adapting through trial and error, only the organism is the planet itself and its trials span eons. The beauty lies not in purpose but in persistence. The humour of it, if one can call it that, is that the Earth might be the universe's most patient janitor. Every 100 million years or so it sweeps the floor, reorganises the carbon budget, and tidies up the mess left by tectonics. From our perspective, that cleanup looks catastrophic. Mountain ranges erased, oceans reorganised, history lost. From the planet's perspective, it's just maintenance. Mountains don't come with warranties. We'll never know exactly how conscious or accidental that balancing act was. Of course, it wasn't conscious at all. But it's hard not to feel some kinship with a system so good at keeping itself within the narrow limits where complexity can thrive. The next time you hold a pebble, consider that it's part of an ancient algorithm, one that calculates stability in units of rock, weather and silence. Imagine this. A rock that remembers something it no longer is. It has been melted, pressed, folded and buried for so long that no trace of its original form remains to the naked eye. Yet deep within its lattice, invisible to the tools of 19th century geology, faint whispers persist. Atoms slightly out of place, isotopes tilted from equilibrium, crystals containing older ghosts locked inside. This is not mysticism, it is metamorphism. Even in erasure, Earth keeps its archive. When geologists speak of metamorphic rocks, they often say they are recrystallized. The term sounds simple, almost neat, as if the planet were calmly reorganizing itself. In reality, it is more like a billion-year recycling plant under pressure. Heat and time rearrange minerals, forming new textures, new bonds, new geometries. Basalt becomes amphibolite, limestone becomes marble, shale becomes schist. But the transformation is never absolute. Inside those new crystals are inclusions, tiny fragments of the minerals that came before, still carrying the isotopic fingerprints of their origin. In that sense, no layer of rock ever truly vanishes. It only changes the language of its memory. Zircon is the best example. The mineral is often described as a geological time capsule, and it deserves the title. Zircon crystals can survive temperatures and pressures that erase nearly everything else. They resist melting, weathering, and even radiation damage over billions of years. A single grain the size of a grain of sand can preserve isotopic ratios that reveal both its own birth and the metamorphic overprints it endured later. Within one zircon, uranium atoms decay into lead, their proportions acting as an atomic clock. But sometimes that clock is disrupted. New zircon grows around the old core, resetting the outer layers while the inner ones continue to keep ancient time. The result is a nested structure of ages, concentric rings of memory, each one whispering a different era of the planet's story. When researchers examine zircons from the rocks beneath the Great Unconformity, they often find this exact layering. The outer zones date to the Neoproterozoic, the time of erosion and glaciation. But the cores inside trace back billions of years earlier into the Archean or even Hadean. These cores are not fossils of rocks we can still touch. They are isotopic echoes of crust long since recycled into the mantle or ground to dust. Yet their presence proves that even when Earth deletes 1 billion years from its surface, it forgets imperfectly. Some fraction of the past always persists. Tiny, stubborn, radioactive, still counting. In metamorphic terrains like the Canadian Shield or Western Australia's Yilgarn Craton, such zircons reveal astonishing complexity. A single rock can contain crystals that record multiple metamorphic events, one at 3 billion years ago, another at 2.5, another at 1. Each event leaves a different isotopic signature, shifts in oxygen ratios, inclusions of rare elements like hafnium or titanium, signs of fluid infiltration or melting. With modern ion microprobes, geologists can now target specific zones within these crystals, measuring time with micron-scale precision. The resulting data form miniature stratigraphies, maps of history within a grain smaller than a pinhead. If the Great Unconformity erased time from the visible rock record, zircons have smuggled fragments of that time forward, hidden in their cores. This principle extends beyond zircon. Garnet, monazite and rutile can also act as microarchives. Each mineral closes its isotopic systems at different temperatures, meaning each preserves a slightly different moment in the metamorphic journey. By combining them, scientists reconstruct not just when a rock formed, but how it evolved, how it cooled, when fluids passed through, how pressure changed over kilometers of burial. The story becomes multidimensional, thermal, chemical, mechanical, temporal. In a sense, every metamorphic mineral is a diary written in several languages at once. We just had to invent the microscopes and mass spectrometers to read them. The irony is that metamorphism, which once symbolized loss, has become a source of revelation. Early geologists like James Hutton and Charles Lyell viewed metamorphic rocks as final states, obliterations of earlier strata, the end of the record. But as analytical techniques advanced through the 20th century, that view reversed. Underneath the recrystallization lies a persistence so profound that it defies full erasure. The deeper the rock, the stronger its memory becomes, because pressure forces atoms into stable configurations, preserving isotopic clues even through partial melting. The more violently a rock is transformed, the more carefully its core holds on to the oldest data. Take the zircons from Jack Hills, Western Australia, the oldest minerals known on Earth. Some are over 4 billion years old, older than any rock that still exists at the surface. They survived because they were recycled through sediments, incorporated into younger rocks, and metamorphosed repeatedly, yet their isotopic compositions remained intact. Within them are traces of oxygen isotopes that suggest liquid water existed on the early Earth far sooner than we once believed. A grain of zircon can outlive oceans, continents and mountain ranges. That resilience turns every erasure into a delay, not an end. When scientists talk about inherited isotopic signatures, they mean precisely this: traces of earlier systems embedded within newer ones. In metamorphic rocks, those inheritances can complicate radiometric dating, producing what appear to be discordant ages, but in truth, that discordance is information. It tells us how many times the clock was reset, how much thermal energy passed through, and how partially the system healed afterward. It is like finding marginal notes under rewritten text, faint but invaluable. If we step back from the microscope, the philosophical implications are subtle but striking. The Earth, it seems, never achieves perfect amnesia. Its transformations are total only at the scale of sight. Beneath that, at the atomic level, continuity persists. Even the deepest subduction zones, where crust is dragged into the mantle and melted, return some of their memory to the surface through volcanic eruptions. Elements and isotopes reincorporated into new minerals, new oceans, new life. This cycle of destruction is also a cycle of retention. The Great Unconformity, then, is not an empty silence but a palimpsest, a rewritten page with traces of the earlier text still faintly visible under the new ink. We can't read every word, but we can see the indentations where sentences once were. Modern geochronology is the art of feeling those indentations, of reconstructing meaning from partial survival. In laboratories today, laser ablation instruments vaporize microscopic spots of mineral, measuring isotopes 1 grain at a time. The patterns that emerge reveal ghost timelines, maps of crustal growth and destruction that fill the spaces once thought blank. Even in erasure there is continuity. Every atom displaced leaves a signature. Every decay event, every trace element, every lattice distortion is a breadcrumb leading back to the conditions that once were. The rocks may look mute, but they are full of whispers for those who listen in isotope ratios rather than sound waves. In that sense, geology isn't the study of stone. It's the study of persistence. We might never recover the full story of the billion years that vanished from the surface, but we can read the ghost of that story in the chemistry of what remains. The zircons beneath the Grand Canyon, the marbles of Greenland, the schists of India, all are palimpsests of vanished worlds. Their cores still carry the music of ancient heat, ancient fluids, ancient stress. The signal is faint, but not gone. So when we look at a polished metamorphic rock in a museum, or run our fingers over a granite countertop quarried from the deep crust, we are touching something that has already lived several lives. It was sediment once, it was magma once, it was mountain once, it was perhaps the floor of an ancient ocean before any eyes existed to see it. And yet, even after all that, it remembers, not in words, but in ratios, in atoms, in subtle chemical imbalance. The memory beneath the memory is what keeps geology honest. It reminds us that disappearance is often disguise, that absence may be a form of storage, and that the line we call the Great Unconformity might be less of a boundary and more of a translation between different dialects of deep time. The Earth, patient and unhurried, never really forgets. It just rewrites. Imagine this. The Grand Canyon at night. The stars stretch from rim to rim, the river hums faintly below, and the canyon walls rise like a cathedral built out of time itself. If you press your palm against the stone, it's cool, quiet, almost impossibly old. Yet that silence isn't emptiness. It's a form of remembering. The sandstone remembers oceans. The schist remembers fire. The missing billion years between them, the Great Unconformity, remembers forgetting. And in that paradox lies the most honest story the planet ever told. Earth has always been an editor of itself. It keeps only what matters to the next version of its equilibrium. The rest it folds, melts, scrapes, and buries. Not in cruelty or carelessness, but as part of a rhythm that has no author. A mountain becomes sand, the sand becomes rock, the rock becomes mountain again. Each iteration slightly rearranged, each cycle a quiet negotiation between gravity, chemistry, and chance. Somewhere in that vast repetition, life found room to exist. Somewhere between erosion and renewal, memory became possible, first in minerals, then in cells, then in us. But it all began with a planet learning how to let go. What we call deep time isn't really about years or eras, it's about patience. The kind of patience that lets rivers carve through continents without ever hurrying, that lets continents drift together and apart as though breathing. The Great Unconformity is one of those rare places where you can see that patience exposed, where you can place your hand across a billion years of vanished history and feel continuity anyway. The gap isn't absence, it's resilience. It's the planet saying, I survived my own forgetting. Every surface of the world carries a similar silence. The polished rocks of Greenland, the ancient domes of Africa, the buried shields of Canada and Siberia. All of them whisper versions of the same story. The planet endures by erasing. And yet, nothing erased is truly gone. The elements circulate, the isotopes realign. Even the dust blown from one continent eventually lands to seed another. The same silicon that once sat in a mountain may now glint in your phone, your bones, or a star forming light years away. When scientists study those vanished layers, they aren't resurrecting them. They're participating in the same feedback loop. The act of looking backward becomes part of the ongoing balance. Knowledge is another form of weathering, gentle, relentless, refining what remains. Science, like erosion, works slowly, polishing away assumptions until only what endures is left. A kind of clarity that doesn't claim to know everything, only to observe carefully enough to keep the questions alive. There's a humility in that, a recognition that even our understanding will someday become sediment. The data we gather, the measurements we refine, the names we give to vanished eons, all of it will dissolve into something else. And that's all right. Knowledge, like rock, has its half-life. What matters is that for a brief geological moment, we got to see the pattern, to stand before a billion-year silence and realize it isn't a void, but a bridge. To feel small, not in despair, but in relief. Because a planet that can endure this much change without collapsing doesn't need to shout its lessons. It just keeps existing. Quietly, methodically, beautifully. Sometimes, when geologists describe the Great Unconformity, they use words like missing, lost, or erased. But maybe those are human projections. Our discomfort with gaps, our obsession with completion. The Earth doesn't share that discomfort. It doesn't miss what it no longer has. It transforms it. The lost billion years are still here, redistributed through the crust, woven into new continents, dissolved into seawater, recycled into the very sediments that buried them. What vanished was only continuity in form, not in substance. The memory beneath the memory is still intact, and that realization changes the feeling of the canyon entirely. It's no longer a monument to loss, but to renewal. Each layer becomes a syllable in a language of persistence. The schist at the bottom, once magma, now metamorphic. The sandstone above, once sand from some vanished shore. Between them, the Great Unconformity, a pause so vast it became structure. If a planet can forget, it can also remember differently. And if it can remember differently, perhaps it can forgive itself for what it erases. There's no malice in the destruction of mountains or the burial of oceans. There's only the slow arithmetic of equilibrium, a system trying endlessly to stay possible. When glaciers grind, when rivers flood, when continents sink, the planet isn't ending anything. It's balancing. It's making room for something new to happen. Standing in front of that, the only sane response is quiet. The kind of quiet that comes when words no longer help, when even questions start to sound too small. Because to grasp deep time, even slightly, is to realize how narrow human urgency is. We chase moments. The Earth measures in cycles. We crave meaning. The planet performs function. And yet, somehow, those two rhythms meet here, in the awareness that we're part of this feedback too. Temporary, yes, but also continuous. The Great Unconformity, in the end, isn't just geology. It's evidence that change doesn't erase meaning, it sustains it. The rocks that forgot are the same ones that now teach. The planet's silence has always contained the next story, and that perhaps is the only kind of immortality that matters, the kind where persistence replaces permanence. So tonight, whether you imagine the canyon, or the glaciers, or the buried zircons still holding their faint isotopic pulse, remember this. The Earth never stopped remembering. It just shifted the archive somewhere deeper than our sight. The silence beneath our feet is full of patience, full of motion, full of memory still reorganizing itself into new beginnings. And maybe that's the most comforting truth of all, that even forgetting can lead to renewal. Even silence can hold continuity. Even loss can be another form of remembering. Thank you, fellow Sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the Sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.